Hello everyone, welcome to this machine learning A to Z, Kaggle and real world projects. In this course, we have added some real-time projects as well as few Kaggle problem solutions so that you can further go ahead and can solve any problem in the competitive world. The motivation of this particular lecture is to give you an idea that what all is expected out of you before you can do this course and what are the prerequisite probably you need to go back and revise. So this course is going to help you with all that section. So right now you would notice that we have multiple projects. Like you can see that we are saying that project 1, this is basically coming from Kaggle. Project 2, this is coming from real world problem, which is going to be some industry related problem and we are going to solve it. Similarly, you would notice that there will be few Kaggle and few real world projects. We are going to add even more project to this because we would like to increase this project number as and when we will go ahead with this, and you will notice more of the Kaggle solutions coming up for you. Now, how this is going to be helpful for you? If you have this dream that you want to go and even personally work in Kaggle, you want to also just showcase your skill set, you want to strengthen all the knowledge by solving some problem in Kaggle, then this course will be very much suitable for you because this will give you all the idea and requirement that what all things you need, how people approach this problem, what all things you need to read from outside whenever required. Not only that, even when you will go and join any industry, then also this course will help you out that in what way the data scientists on daily basis are solving their problems, what kind of problem they are facing, what is the solution they are posting for them. All these things we are going to learn as a part of this course. Now, one expectation from my end would be that when you're looking at any problem, please do not directly jump and look at the solution. Always first try to solve that problem on your own. It may be it's going to take some time because all the projects, especially which are coming from Kaggle, they are time taking projects. So you have to spend some good time in exploring that. But once you do it on your own, then only you will be feeling more confident when you will look at the solution. So your learning will be far better comparatively. Now, the prerequisite for this particular course, definitely we are going to expect that you should already be having all the machine learning language. So that is something you should be aware of, all the algorithms, everything you should be well aware of. This course will be completely in Python. So when I say machine learning, so even if you're coming from R background, it is not going to much impact you because it's more about the knowledge which you will be gaining from it. So it's not going to impact. Maybe if you're coming from R background, R language background, you can always go back and convert this code to R language. That's something you can always do. But knowledge of ML is must. One suggestion which I can give you out is you can look at our course which is called as Machine Learning A to Z Become Kaggle Master. This course, you can use it as a prerequisite course. Once you complete it, you will be all good to come and start solving these particular problems in the further course. So I can say that this course is like an extension of that particular course. Now, so this is all it which I want to mention. So best of luck now. So you have to start looking one by one. And also one more suggestion I do have is please solve all these projects in a sequential manner. Because you would notice that I might have given a lot of explanation in maybe project 1 and I have used all that concept in project 2 or project 3. So there's a possibility of that. So that's the reason my high recommendation would be that if you can solve all this problem in the sequential order, that will really make your life a lot simpler. In this case study, we are going to work on a medical problem. This is a real problem which was faced into the medical industry. And in fact, this problem was posted on Kaggle, uh, so that all the data scientists can come and basically try to come up with a solution. So we are very thankful for this institute to provide us the real data set so that we can use it for research and development and for our learning purpose. In this problem statement, basically a lot of manual efforts was happening earlier, and they wanted to replace it with machine learning automation. And we will learn that how to do it, and we will take step by step for doing so. When I say step by step, we are going to work as a complete data science uh, person, where we are going to start this problem from analyzing the data, cleaning up the data, thinking about how to even give a kickstart to a machine learning problem, identifying appropriate solution for it, and then working on it. And remember, it's a real data set, so there are definitely few issues which we have to tackle here. Let's understand the problem statement first. So since this problem is from Kaggle, let me take you directly to the Kaggle page, and just to make it appropriate, I have given you the Kaggle link from where you can directly go and understand the problem statement. But I'm going to give you the whole explanation for it. Now, to solve this problem, you definitely don't need to be an expert into medical side. Even I have no experience in medical domain, and whatever I have learned is just to solve this particular problem. So even this is a very common thing which gonna come as a machine learning engineer, that you may not be an expert into a domain, but you are still solving that problem of that domain. So this is quite interesting about this machine learning journey. Now, let's understand that what is this problem statement and how is being solved. Now, as you can see that this problem is provided to you by this Memorial Slogan Cancer Center, MSKCC. This is a very famous kind of center basically into the medical domain, and this was even accepted in NIPS 2017. So it's a very famous part. And this problem also had an award, like whoever is going to give them the best solution, they were awarding that particular candidate with 15,000 US dollar. Right? So this will also enable you to kind of uh, go and even target these Kaggle competitions later. What I mean is that um, if once you solve all of our case studies, because what I am going to do is I'm going to give you both the side, how a problem is usually being looked at in the industry and how a problem is being looked at from a Kaggle point of view. So you should know the real difference between them, because definitely Kaggle being a competition, there will be some sort of criteria based on which you have to provide your solution, so that it will make the life of Kaggle people easy to identify who is the winner or who is not, right? So but in real world that's not the case. It goes in a little different variation, and I'm going to give you all those insight while working on the solution, so that you get an idea that how this differentiation also comes in terms of solving a Kaggle problem and solving the real world problem when you work in a corporate world. So to start with, so if you look at this problem statement, so what happens is we do have something called as gene. Okay, so there is something called as gene, which is, you might be hearing this from your biology term if you do remember your biology course, that you may have a gene sequence with you. Now in every gene, if there is any variation which gonna happen, so this can lead to any sort of cancer. Okay, now definitely it's not mandatory that all the tumor is going to be kind of a cancerous type, but definitely it can have some sort of cancer. And in this problem statements, let's say we are taking the 9 classes of those cancer, which is going to be from 1 to 9, okay, or 0 to 8, sorry, basically whichever way you want to take up. So this is going to be the class of my cancer. Now, what happens is we do have basically the pathologist who is aware of a lot of genes and their variations, and they know about, okay, this, if this is the gene, this is the variation, then this basically belongs to this cancer tumor. But what happens is there are thousands of mutations possible. Now, with respect to this, the challenge is that there is a lot of research paper being available for each variation for each gene, right? So now for each gene itself, there will be a lot of variations possible. Now, what happens is there will be a lot of research paper being available for you, and from those research paper, what pathologists have to do, when I say pathologist, I'm talking about a domain expert. Okay, I'm referring to a domain expert who have to, let's say, look at, let's say a gene is there and a new variation comes up. So that domain expert have to go and read a lot of text, a lot of research paper, and from that they kind of go ahead and identify that, okay, this belongs to maybe this sort of cancer. And this is actually happening in real world. Actually, pathologists are spending a lot of time in kind of getting the answer of, okay, where this is going to belong to. And that was the main challenge. Now, it's very easy to get all those research paper because you can go on Google and just type, okay, this is the gene, this is variation, and you will get a lot of research text about it. So collecting the data is never an issue, but going through all those research text and then basically getting to an answer that, okay, this belongs to this probably cancer class, is very difficult, because then you have to spend a lot of time, enormous amount of time in going through it. Now, this is where we want to bring our machine learning in. What we want to do is we want to replace that manual process of that domain expert with our machine learning. Now, this is actually what the main trouble they this basically particular center want to solve, and that's the reason they wanted to make it as a competition, so that if anybody gives maybe the best solution, they might want to use that particular solution for basically for their future purpose. So that's what we have to solve. And the funny thing about this whole solution case study would be that we have no idea, including myself, that what is this medical domain. We will not even be having any idea about what is this gene thing, what is this variation, what is this research paper talking all about. You may not be able to even understand if you will try to go through each and every detail of the text, but still you will be able to automate and will be able to give the answer that, yes, if this is the particular thing, that then I will create a algorithm or a machine learning model which will tell me up, okay, this belongs to this class. And thus you can imagine that how much of the time you're going to save while doing so. So this is a very fun problem, and we're gonna understand it from the machine learning point of view as well, that we will try to understand that, okay, how this is going to fit in from a machine learning criteria point of view, and what exactly we need to solve it, where does this fit in, everything we are going to talk in detail in the next video. Okay, so now let's understand that what are the things you would need to solve this problem completely. Now, first thing is you need the data. So in order to get the data, you have to first create an account from Kaggle, which you definitely need it here. And once you're done, you can go to your data tab, and from here you can get these two files. One is your training text dot this part, and even your training variants dot zip. Okay, so this will be a zip file. You can unzip it and can start working. So these are the two files which you need to work on it. So again, repeating, you have to get training text dot zip and training variants dot zip. These are the two files which you will need to work on this part. Now, second thing is that once you get the data, you should always look at the discussion forum. This is one of the place from where I learn a lot personally, and I would definitely recommend all of you to please go ahead and kind of look at the discussion forum. There is a lot of discussion which keeps on happening between people, like they have some doubt, maybe that's your doubt as well, and there will be people answering that, okay, if you get stuck in this place, then how you can proceed, or you can post your questions and you will get very interesting answers. So this is one place from where I have myself learned a lot, and you can even look at the leaderboard who is working on what. And this is the things which you will definitely need to work on this part. Now, in this discussion forum event, you can see that this Iker, this guy is, I think he's the organizer of this. So you will get to know a lot of understanding about the problem statement. So it do happens a lot of times that when a problem is given, since you are not even a domain expert into, let's say, medical domain, so these organizers comes and kind of give even more detailed explanation about the problem. So, or if you are not able to understand it, then you can really post it out and they would really help you to understand all the problem statement. So this is an interesting thing about it. So I would strongly recommend you to go through this discussion forum. Secondly, even I would like to credit a lot of people who have even contributed to their solutions. In fact, a lot of solutions I have personally gone through in GitHub accounts. So it's very easy to search for them. You can just go to Google and type this problem statement name and type GitHub. There will be a lot of people who will be putting their own solutions. In fact, I would like to credit all those people who have put their solutions on basically GitHub, because even from them I have learned how to solve this particular problem, and using that knowledge I was able to design a nearby solution to it. So I would not say that this is completely coming, the whole solution is completely coming through me. In fact, I would wholeheartedly thanks those people who have given the best solution into the GitHub accounts, and I kind of looked at them, learned through it, and created the one of the whatever the better solution I could think of, and kind of providing it to you, so that you can even think like a winner, that how generally even winners of Kaggle thinks and approach the solutions, and why basically they were able to win that competition. Because even the people who kind of win the competition, they post a lot of solutions on GitHub, and that's a very good way of learning something. Never feel shy even once you become an expert into this domain. Never feel shy to even learn from other people. That's one of the very good idea in machine learning. Even today, I have developed this habit of going through at least one or two GitHub accounts on daily basis, and try to learn their solution, what is their approach, and sometime I just feel, wow, what an excellent solution this guy have given. So I would recommend you to do that. Now, once you get this data, and this you need to really understand that what is this data first. Let's explore this, and then I will explain you that given this data set, once we understood that, what is this real machine learning problem we are trying to solve, right? So we need to really fit in this problem into the machine learning box, otherwise there's no point of solving it. So we need to really fit in all these things into machine learning part. Now, one thing which even we have told in the kind of in our introduction video also is that we are kind of assuming here that you guys already have the machine learning knowledge. If you don't have it, you need to go back and kind of learn that topic, because this is an advanced level course where we are expecting that you really know that what is supervised learning, what is the unsupervised learning. This is called as classification, this is regression. So at least we expect you to have the basic knowledge of machine learning. Any advanced level concept which we are going to introduce, I'm going to give a detailed explanation of it, so you need not worry about that. So for anything which we feel that yes, it makes sense for us to kind of give you the solution of, or give you an explanation for that particular topic, we are definitely going to do that. So you need not worry about any advanced topic kind of solution, because we know that generally when you walk through any course, what are the things generally instructor kind of cover, and what are the things instructor do not cover. So but I'm really sorry to say about this, when you go to the real world, a lot of things which people do not cover is really important, and you will really notice this while working on this first case study itself. Means when you will solve further, you will realize much more things to come, but at the same time you will learn about it, that definitely there are a lot of important things which maybe books will not teach you. The beginner level books, or maybe the beginner level instructors, will make your life easy to understand what is machine learning, but at the same time those complex details will be kind of skipped out. So we want to bring up all that, because we do want to bring up all the experience what we have learned while solving those real-time projects, so that you do not face that difficulty once you move into the industry. So with this, let's start understanding the data. Let's start shooting, at least get an evaluation, get some insight on that data, and then we will try to convert this problem into a machine learning problem. Now, going ahead with this, let's first analyze the data. So, yeah, this list seems to be huge, but yes, you do need all these packages. But I would strongly recommend, in case if any place you get an error, because it's a high probability if you execute this import statements, you may end up with a lot of errors here. But really do not worry about that. As in, when you get any error, you know how to install those packages. You just look at those packages name and say pip3 install package name or conda install package name, right? So whatever way you have done your installation, just do that. So no need to worry. So even I have put this comment as well: if any of it failed, do not panic and just use this commands. I've given you the commands and all. Just look at the error and accordingly just install it, because there's a high possibility that you might not have already all these packages being available to you beforehand. So it's a very common case. No need to worry about it. Once you're done, then the second thing would be to kind of load this data set. Now, once you have downloaded this data set, you, let's say, have created a folder. So what I have done is, like, we got these two data files, right? I told you two zip files, training variant and training text. Now what we are going to do with this is, I have unzipped them and created a training folder, and inside that training folder I have kept both these files, okay, so that I can just go ahead and start using them up. Now, one thing is that this, we are going to use pandas. So again, we are going to read it by using read underscore CSV, and the first file will be loaded as a data frame, and the data frame name is data underscore variants. The second data file was training text. Now here, if you will go and look at the data is separated by a delimiter like this. Okay, it was not separated by a comma. Like, if you look at the training variant data set, it's going to be separated by comma. So I need not define the delimiters and all. But here in this data set, I do really need to define this. So that's the reason you can see that, and we do have like ID comma text to it. Now let's go ahead and try to explore this data. Okay, so let's see that what all is going to be present inside this data. Now, in order to get that, so first what we are going to do, let's explore the data variant file. Now in this data frame, as soon as we did a head, we can see that we have ID, gene, variation, and class. Let's understand that. Now, this is the class we were talking about, right? So I told you that there can be cancers of various type, which means the cancer will be from 1 to 9, okay? And this is where we are interested in, that given something new coming up for you, you want to basically look at the gene, the variant, and the research papers associated with it, and you should be able to tell that, okay, this is going to be my class, right? Now, here in this data set, I do have gene, I do have variation, right, which we have talked about. But I was telling you that we do have gene, we need variation, and we need the class, right? Sorry, research paper, which let me call it as text. And then we are interested to predict about class, right? This is what the problem we want to solve. Given any new gene, the variation associated with it, and the research paper, like all the text data related to it, and I want to predict which class it belongs to. Now, in this first data, I do have gene, I do have variation, and ID basically it tells this ID is also there for to link the mutation to the clinical evidence, right? So this is what we do have. So definitely in the second data, we will be having all that text information, which is going to be coming from the research work, right? So this is how the data was collected and given to us. So let's go step by step. Let's not hurry up in understanding this problem statement. Now, the second thing is that, so once we are doing this analysis, when we look at the information here, so we can see that we have ID, gene, variation, how many non-null values are there, every detail is mentioned here. Let's do a description of it, and we can see the mean, median, 25% percentile, maximum, minimum, all these values. You can very easily do that. Now, then you can look at the shape of the data. This shape is telling me that how many rows I have in my data set and how many columns I do have. Now, definitely when we talk about column, we do have columns like ID, gene, variation, class, right? It's 4 columns. That's the reason you are seeing this value as 4. And I do have 3,321 entries into my record. Now these are the column, right? So as I just said that we have 4 columns, so we can see it with the help of columns function. Now let's explore about data text, means my second file where we do have the text data coming up. Now here you can see we do have ID column and the text. Actually, if you look at this text, this is going to be huge data. I would strongly recommend you to open that file, data file, and see that. It's going to be a huge data. And you will notice that it's a research paper, so it's going to be huge text being associated. But one interesting thing you can notice that ID is common between both the data set. So I can definitely do a merge operation, and then I will have gene, variation, and text, all things together. And using this, I will be building my model, and then later we are going to kind of, for any new data, we're gonna look at our predictions. That's what we're gonna do. So let's look at again some more information, like we can do an info again. Can you notice something interesting here? This information is giving us some idea. Can you identify that? If you look at it, this is giving me an idea that in text we do have some missing values, right? Without doing any analysis on this data, we can still analyze just by looking at the info that yes, we do have some missing values. So we will see that how to deal with that later. Now let's go ahead and understand few more things. We can do a describe again to try to just do some statistics for the data. We can look at the column and we can look at the shape. So in short, my data set looks like this, right? So if you look at this data variants, this included my ID and gene variation and class, and data text includes my ID and this research paper text. Now in further videos, we gonna go ahead and try to understand that what we can do with this data, and how really, what is the kind of problem really now we are going to solve, right? So we first understood that yes, this is a Kaggle related problem. What is the real problem the people were facing and why they want to automate with machine learning. Then we looked at the data set, tried to explore it by using our pandas data frame, and got some insight about the data. Now the next step would be we will try to infer from this data set or this problem that how basically it fits in the machine learning world. What is the real machine learning problem we have to solve further. So that is the one next step we're gonna follow. Okay, so now once we got the understanding about the data, now let's understand that what kind of problem we are trying to solve here. So we are interested in predicting about the class, right? So the class will be between 1 to 9. So it can be 1, 2, 3, 4, 5, 6, 7, 8, 9. And we have just got this value by looking at the unique values from the class column. Now, if you look at it, this is a discrete output, right? As soon as we see that it's a discrete output, we say that it's a classification problem. Now the second question is it a binary classification problem? No, because in binary classification problem, we can have possibly only 2 outputs. And here we have more than 2 outputs. So this kind of thing is called as multi-class classification problem. So we are actually trying to solve a multi-class classification problem. And that's what the prediction model we are going to build here. Now, let's try to understand that from the real world perspective, what are the things really important for us while building our model. So what are the things we need to keep in mind while trying to build this model. So number one thing, so when we are trying to build this model, definitely it's a medical problem. Now in medical problems, the errors can be very costly. Imagine there's a patient coming to a doctor, and a doctor tells him up by looking at maybe his gene and the variant, well, basically mutation, and tell him that, okay, most likely you have this cancer, you are in this cancer stage or whatever. Now, and if his answer is wrong, that imagine what's gonna be the impact on that patient. He may even sue the doctor. So the errors are going to be very, very costly. So we cannot afford errors. We have to make sure that we do take care of that error component to bring it very low. So my accuracy is going to be highly important here. So in this case, we may want to return the result in terms of probability, because if you think about this, maybe we only want to give an answer in terms of yes to a patient, that yes, this looks like to be more appropriate answer here. So we may want to put a probability to it. Let's say if the probability of my answer that okay, this most likely you are going to have this sort of cancer in, let's say, category 3, is, let's say, if I'm telling that with, let's say, 99% probability, I'm more confidently I can say that yeah, you have basically, let's say, type 1 or type 2 or type 3. So we can tell it like probability that you are falling into class 3, and basically given that you have x1 is your input, right? So x1 is nothing but you have your gene and you have your variance of this sort, or maybe the research paper for this variance is this, because we can easily get that research paper information from Google. So my gene and variance is this. So given this information, then if my, let's say, probability is coming out to be, let's say, 0.99, which is 99%, we can very confidently say that yes, you have possibly this sort of problem. But let's say if this is not coming out to be 0.99, but it is, let's say, 0. Maybe let's say 0.4 or 0.5 or 0.6, something like that, right? Now in this case, we are not really very confident on our answer, because if you look at the answer now, though this 0.5 may be a higher number in comparison to the other 8 classes, because maybe the other 8 classes might have 0.1, 0.02, 0.05 like this, which is contributing to the remaining probability. But still this number is ambiguous, or there is a possibility that maybe for if I look at this, maybe I'm getting a probability of basically y belonging to class 3, as where the input is x1 is 0.6. Maybe there's another probability of class 2, which is given this x1 coming out to be 0.4, and maybe the remaining all the probabilities are 0. So here also it's an ambiguity that where we should place it in, whether we should look forward for whether we can tell to the patient that you belong to class 3 category, or whether you belong to class 2 category. So maybe in this case we may want to look at more evidence to give some basically final solution to my client. So so that's the reason I think the probability will be very important factor here. So in order to be more confident to avoid the error, we will be looking at our solution with respect to probability in this case. Okay. Now, one more thing which we can attach to build more confidence to is maybe telling the basically the reason. If my algorithm can even reason out this very well, that most likely if I'm telling to my patient that okay, you have class 3, then these are the evidence for it. I'm telling basically the reason that why I'm telling you that you belong to class 3. Maybe there may be few terms which I can use and say that okay, since you are falling with this thing, that's reason you are falling into class 3 category. So what does this mean? Means interpretability. Can my machine learning algorithm also tell that why it thinks that it belongs to class 3? So there are various algorithms which can help us in answering that. So there are few algorithms which basically tells those answers, and there are few algorithms which do not tell those answers also. So there are both sides of stories. We will see to that what are those algorithms which are good. For example, if I talk about your RBF, and basically I'm talking about SVM, this is highly non-interpretable. So if we have done a machine learning course, you might have learned it, but if not, we will go through some of the case studies and you can see that how it is not or how it is. And similarly, if I talk about a lot of other algorithms, for example, if I say naive Bayes, if we say decision tree, we say logistic regression, even linear SVM, right? So these are highly interpretable algorithms. These also can return you that if there is some sort of prediction happening, then why that prediction is making sense. So those sort of things also it can return. So it's very important for us to basically tell an interpretation of behind my prediction. That's is very important part which we want to also solve. Now, talking about the latency or time taken to return a result. Now, definitely, since I want to reduce the error, so maybe I can give some flexibility to the time part. My algorithm may take, if my algorithm is taking, let's say, a few seconds or few minutes to give an answer, I might be okay with that. Yeah, if my algorithm start taking maybe an hour, then it's might be an issue, right? Oh, sorry, one day, then it might be an issue, right? So it depends on my business requirement as well here. But most likely I would be okay if my time taken by that algorithm is okay, means if it is reasonably kind of manageable, I'm okay with that. Maybe like if you think about like companies like search engines, right? Internet companies like Google. Now, there basically the time is a very critical factor. If you say something, they want to immediately get an answer and give the output to you. The prediction algorithm required a very fast latency, should be very low. But here, I don't want my latency to be that low. It's okay if I take some time. So that's also one thing we can keep in mind while building models, because there are some machine learning algorithms which do take a lot of time when the data is huge, which you might have also learned during your course, like KNN algorithms and all that, which do take a lot of memory, which do take a lot of time. Basically, in terms of if you look at the order of complexity of those algorithms, it is high. But maybe in this case, in this particular kind of case study, maybe they fit quite well. We will see that if they really fit or not. But maybe if they take a little bit of extra time, I might be okay with that time frame. So that's also one thing which we have. And I have written all these points in detail for you to again go back and revise if you wish to. So these are the things which I just explained it to you. Now, it's highly recommended that before you start looking at this solution further, I have given you a detailed explanation about the problem, about a data set in machine learning, how it fits in terms of we are going to solve a multi-class classification problem. And even we understood that from the machine learning points, what are the important factors we need to keep in mind while solving this. So given all this knowledge, can you go ahead on your own and see that if you can come up with a solution on your own? I would highly recommend to pause it here. Don't go ahead and try to solve this now problem on your own, and later come back and start looking at the solution and enjoy it, right? So then you will realize that, okay, what are the things you were missing out, and then you can anytime come back and look at the things and start working on that. So with this, best of luck for all of you who are solving this case study, for solving it first on your own and then match up a solution. Thank you. Now, I hope all of you have already gave a good attempt before looking at the solution. But now let me explain you that what my solution is, and definitely your solution might be quite different, and maybe you have come up with a better solution than me. Uh, in fact, if you have it, you are welcome to post it on the discussion forums and all that, so that even others can take the benefit out of it, or even I can answer to your response. It would be a great thing for others to, even for myself to learn. uh, so let's look at it, but I can tell you that this solution is also kind of a leaderboard solution, so this is a good solution to look at. Now, here, basically, if you look at this, we definitely, once we get the data, if we have to first bring it to a form that my machine learning algorithm can understand it and can work on it. Now, there is a problem. Problem is we do have, if you remember my data, we do have a text data, right? So if you do remember, we have even loaded this file, right? We have ID comma text, and I told you that this text is nothing but like a research paper. Can you see that? It's a huge text kind of research paper kind of thing. Now I cannot feed in this kind of paragraph kind of text to my machine learning algorithm. So if you have gone through the sections of NLP, basically in machine learning topic, you might have learned that how to process it. So we are going to use that. So we need to convert it to a format so that my machine learning algorithm will be able to deal it. So before that, we definitely would like to make sure that my data first come into a format. So we need to do some processing on it. Now, which will include few things. For example, if you look at this text data, there's a You can see that I do have let's say some lot of numbers. Maybe I don't need them. These numbers are not required. Even I might have a lot of like is, and, in, the, or what I will do with this word. These words may not be much relevant, so these are called as stop words. Maybe I would like to remove them up. They will be, since it's a research paper text, there's a possibility that maybe somebody have, instead of giving one space here, he might have given two spaces, or maybe he have pressed the tab. So those things also might not be that really important for me, right? So if I look at it, there may be various places where we may want to remove all those unnecessary portion which may not be relevant for my final analysis. So that's what we're going to do that. So in order to do that, we have first written a function which will help us to process once we pass this text data. Now, as you can see that this text data uh, is kind of huge. So when we will run our function, it will take some time. Okay, so you have to be a little patient on that part. So let's go back and see to this, that what we have to do. So number one thing is that we have used this NLTK library to got all the English stop words, because my research paper, which was in text format, is basically in English characters. So that's the reason we got all the is and a, the kind of words, because we definitely would like to get rid of it. So we have written a data text process function, and you can see that I'm going to call this function where I'm going to pass basically the text column. And basically here what all we are doing is we are looking at if it is a string, means it's not an integer, because as we've just learned, maybe that 2.2, 3.4, those numbers may not make much sense in terms of my final output. So that's the reason, if we are looking at that, then first thing is we are interested only, let's say, in this. So we are going to basically replace all the special characters and all that, because definitely those things also we don't need. If we do have special characters, it's of no impact at the rate what it will do to my final analysis. So similarly, if we have like multiple spaces, like I just explained you, if you have tabs or double spaces, we would like to remove them up, right? So we are replacing that with a single space, the tab with a single space, so that everything comes to a normal format. And we also have to do this. Yeah, it's very, sometimes it do happens that somebody have written, let's say, something like gene like this, and somebody else might have written gene like this, but they both are same, right? So in order to bring them in the same scale, we will lower case or uppercase the whole text, so that now everything comes to a same scale. So that's one thing we can again do here. So we will do it with the lowercase. Then further to that, we gonna split to each word and gonna make sure that we do not consider stop words like a and the. So we are going to remove all of them here, right, in this particular function. And in the end, we are going to return it, and that now my final text is going to be my pre-processed string, which we really needed. So this two code is basically doing that. So I have given the proper comments and all that here, so that you don't face any difficulty in understanding this particular function. So do not worry about that. You can anytime go back and just play with this particular code. Now, then after that, we definitely need a final data frame, which is going to be a merging of the data frames of both sides, because if you remember that ID column was common between both of them. So I'm gonna merge it with respect to ID column now. So I'm gonna do basically this part on ID column, and you can see that now I got a data set which have gene, variation, class, and this text. And this text definitely going to be huge, though it's not showing up here. Now, the next thing is we definitely want to look at if we do have any missing data, because missing data can impact our analysis a lot. So we have to make sure that the data which we have is in appropriate format, which we can use it. So we may want to make some decisions if we notice that we do have some missing values. So now we can see here that yes, we do have some missing values when we hit this line of code. Almost there are 5 rows which have missing values. Now, what to do with this missing rows, right? So one idea could be that you can just go ahead and remove those rows because they are very less in number. But we do have a very small data. If we have some 3000 plus rows, it's not really a huge data with us at the moment. Now, in this case, we may want to come up with a better idea. Can we do some sort of imputation here? Imputation means that can I replace this nan with some more appropriate values? Now, what can be that appropriate value if we want to do that? So in this case, one idea could be that we can just take up the gene of that row, and the variation means, let's say this is nan here. So we will just replace it with the concatenation value of this gene and this variance. So that's what we have decided. Again, this strategy is completely up to you to decide. You can take your own call. If you want, maybe you want to remove those rows, or you may want to come up with a different imputation strategy, please feel free to do that. This is just one of the strategy I've taken, but it doesn't restrict you from taking any other strategy. Feel free to take any other strategy as well. And after you have done this imputation, again you can have a check that whether you still have any missing value. And you can see that since this is got properly imputed, now there is no missing values left with us. So we can definitely go ahead and start working on our further analysis. Now, once we have done that missing value imputation, the next step is to work on splitting this data into training, test, and validation part. Now, this is really important because if we build the whole model just based on the basically on the whole data, then there is no way that we can validate it. Now, one idea could be that we can just go ahead and create a training set and testing set, which you might have learned in a machine learning course, and create a model on training set and test it on a test it on the testing set. Now, this is also sometimes not a good idea because a lot of times, especially when we play with hyperparameter tunings, we do kind of we do get the results which comes out because of my test data set, and because we start looking at the test set and we start keep on improving the accuracy on my train set, so we kind of start getting a dependency on the test set part. Now, in order to handle that, we come up with a validation set. So what we start saying is that we can split now the data into three parts rather than two parts. And those three parts is going to be like, we gonna create one part for my training set, second part for my cross validation set, and the third part for my testing set. Now what we're gonna do, we're gonna build and verify our model with the help of these two. Okay, think of cross validation as the test set only. Now here with the train set, we're gonna build our model, and with the cross validation we gonna do the hyperparameter tuning and all that, and we'll see that what is the best parameters or metric we're gonna get out of it. And once we get this, then once we have the final model based on the testing of cross validation, then this is completely untouched data. We have not yet used it for anywhere. So we will finally validate our model output with this test set. So that's what we are going to follow in this particular case study. Now, the first question is which is going to come to your mind, that how should split this data. So there are various ways people go for it. Some people take it like 60-20-20. Some people take it like 70-10. So basically 70-10 and 20. Depends on you how you want to take up. Depends on how much data also you have. What I have taken in this case study is that I have first divided it into 80 and 20, and this 80 again I have divided into 80% and 20. So which brings us to kind of this sort of data. So this cross validation will be 20% of this 80. So that's what basically how we gonna divide it. So first we gonna write a code which is going to help me to convert into train and test, which is 80-20. And then again on the train data set we will again do a split on 80-20, and that 20 we will give it to cross validation, and 80 we will give to our training data. So that's what the strategy we're gonna adopt. So let's see how we have done that. Now in order to do this, what we have done, you can see that I'm using this train test split function, which is gonna first divide it into 80-20, and this is gonna return me train and test data. Then further to that, we are going to use this train data and again gonna do a split of 20. So we're gonna get the cross validation data now, right? So we got three set of data. One is cross validation, testing data, and training data. So three kind of data what we got. And if you want to look at that how many rows and columns you do have now, you can always look at it by saying shape, and this is going to tell you that in your training data you have some 2124 records. In your test data you do have 665 records, and your validation data have 532 rows. So this is how we can see our data. Now it's very important point that when we do this splitting, now we always want to see that the data distribution have happened kind of properly. Because we can end up with a lot of issues if we don't have. Imagine I have taken a training set, okay, which because if you look at it, I have classes from 1 to 9, right? Now there is a possibility that in my training set, I have taken all the data for my, let's say, class 1, okay. I have taken all the data of training here. But in my test and cross validation, I have no rows left out because it's a random splitting. So maybe there's a possibility that in my cross validation and test, we have no data related to class 1. So there is no way to even go and verify whether my model, which is bringing this class 1, is good or not. So now this can be an issue here, right? So we definitely want to make sure that the distribution have happened appropriately, and that's what we're going to look at. Second kind of problem could be that maybe there is a class 7 which maybe not at all present in my train set, or very less amount of data have gone here, and more data is going in my test and my cross validation. So in this case, we don't have enough data in the train set in that case for that particular class to learn a particular pattern, a good pattern, and give prediction. So that is also a bad strategy. So we may want to look at if there is any issue, we again will go back to the basics and again kind of look at again the split and all that properly, so that a distribution happened in the right format. So let's go and see that how we can verify those things up. So in order to do that, what we have done, we have got our training class, testing class, and CV class distribution. And what we have done, we are looking at the classes because that's what is our main worry, that each class should be distributed kind of in a appropriate manner. So what we have done is we are looking at if you look at this code, what this is going to do, it's going to look at that class 1 is in training set, how many times it is coming. So let's say 363 entries of class 1 is happening in my train set. Similarly, class 2 have 289 entries in my training set. So like that, we're gonna get the output for train, test, and cross validation. So this is what we are going to get from here. Now once we are done with this, now definitely we can I can even look at the test class distribution, I can look at the CV class distribution, but the problem with this approach would be that it will be very difficult to look at the raw output and kind of do a comparison. So what is the best way? As a data scientist, you should be kind of visualizing this. You should look at the graph, right? So if you can put this things into graph, it will be more easy for you to visualize how the distribution is happening. So for doing this, we have plot this particular graph. You can see that this is happening for your train class distribution. So we are drawing the bar plot, and here you can see that for class 1 we do have a good distribution. For class 4 we have a good distribution. For class 7 we do have a very high distribution happening in my training set. For class 8 and class 9 we have very less data coming into this. So let's see what's the case in my other portions as well. But before that, maybe I want to put it in form of percentage here. Like if you look at it, class 7 have the maximum data in my training set. So what I've done, I've written a code to return the percentage of this, that what is the percentage of overall of class 7 in the whole data. So it is almost like 28.672 percent of the data which is coming in the train set for class 7. Similarly, for class 4, we have 20.669, and this was quite easy for us to do that. It's a very simple Python code to get all these values. You can go through it. So this is how you can see this distribution here. Now let's go and check the distribution for my test part. Now for test also, we can see that for class 7 the distribution is high. That means maybe in our original data set itself, my class 7 have huge amount of entries. So even for class 4 we have huge, and for class 8 and class 9 even we have lower number. And you can verify that from this as well. So class 7 we are getting 28.722, and you can see here also in the train set we have almost the same distribution, which looks like if you compare basically both this output looks like my random split have happened quite well, right? Let's look at the cross validation, and here also we are getting almost the same output, right? So again, class 7 is very nicely distributed. 8, 9 have very less distribution. Even if you compare for the rest of the class, you can actually check that it's going to be kind of in the same distributed manner. As I said, sometimes it can happen that this distribution is not happening properly or in the same way. In that case, you need to go back and again rework on this. Okay, so don't just blindly start working on any machine learning algorithms. Always keep this in mind. This is a very critical fact, guys, that you have to look at before you even think of machine learning algorithms. You should always look at your data and see whether before you plug in your data to machine learning algorithm, everything is in the right format, whether you have cleaned it. All those things are really important as a data scientist for you. Otherwise, you may end up with some messy results. Okay. So we will see the further points related to machine learning now in the next video lecture. Okay, so after we have done all the cleaning, we have looked at the data, we have got our training set, testing set, cross validation set. We have even confirmed whether my distribution is appropriate or not. Now, after this, we need to go back and see that what is the criteria based on which Kaggle is going to decide that who is going to be the final winner. Now for this we have to again go back to Kaggle page. So I'm going to go on the top, click on this Kaggle link once again. Now when we are going to look at this, you will notice here there is something called as evaluation. Now let's click on this, and this is where you need to see that what is the criteria they have kept it. Now you can see here that they have clearly mentioned this is going to be evaluated on multi-class log loss. Okay. Now you might have heard about various ways of evaluating a model. For example, you do have something called as accuracy, right? This is a very common metric being used. You have something called as AUC, area under curve, ROC. So many things are there, right? So many evaluation metrics are there for my model. But in this case, Kaggle have kind of restricted you to multi-class log loss. And this is how your Kaggle competitions go different from your real world corporate problems. In the corporate problems, there is nothing like this, that you have to only look at one particular metric and give the output. You need to be kind of generic, but Kaggle being a competition have to definitely go in a way so that they can easily identify that who is the winner. Now, this log loss, if you don't know about it, don't worry about that. I'm gonna give you a good explanation of what is log loss, because I know that most of the instructors generally don't teach this metric. If you know it, well and good. You can skip out this particular lecture because this lecture is going to be completely about log loss. But if you don't know, then you will learn that even from this problem point of view, what are the things in log loss you look at. So we will understand this particular point and how this log metric is important. So maybe I would keep two metric here. One is your confusion metric because that's what you guys understand well. So I'm also gonna consider confusion metric so that you can understand the accuracy portions and all that quite well. At the same time, we will also understand from the log loss point of view, because the winner is gonna have the minimal log loss. So here, like we always say that this, right? We want to keep the error to the minimal point in machine learning. So similarly for log loss, we want to keep the log loss to be minimal because that's what would be our evaluation criteria here. So that's what we're going to learn now. So let's understand that what is first log loss, and then we will relate to our problem statement that how this is going to fit in this log loss formula here. So let's go back and understand this now. So this is going to be log loss. Okay. So in order to understand this log loss, let's take a very simple example. Okay, so let's say I have input x, okay, and I do have the output y, and let's assume that this is a binary classification problem. So let's say for my input x, there is something like x1. In fact, let me mark it with different color, and let's say my original output for this is 1, x2 this is also 1, x3 this is 0, x4 this is 0. Let's say this is my outputs. Now here, let's say when I build a model and I got my prediction y dash, okay, this is probability. Let's say my probability came out to be, let's say we have built a model that anything greater than or equal to 0.5 probability, I'm going to mark it as 1. Otherwise, I'm going to mark it as 0. Let's say we have built some model like that. And for the first portion, let's say we got it our probability as maybe 0.9. Second one I got 0.6. Can you see that it's a close decision because we have just a probability greater than 0.5, so that's why we have considered it. Third column is, let's say, 0.1. This is good for predicting it to be 0, but let's say 1 is 0.4. So if you look at this part, this is, let's say, 0.4. Now, let's say these are the probabilities, and based on this, you have done your predictions. Now, if you go with your accuracy metric, and if you have built something like this, then in that case, your accuracy will come out to be almost 100, right? So that's what you would say, that my prediction and my final output is quite good. But log loss kind of work in a little different way. Let me first explain you the formula behind this log loss so that you get an understanding that how it works. So in order to get the formula, I will explain you how this formula also works, but for now just let me note down this formula, log loss. So for the previous data, first of all, it's going to be minus, okay, minus 1 by n, okay, means I'm going to take the average. So if I have, in the previous I have 4 rows, so my value of n is going to be 4 in that case. I'm going to run this from 1 to n, okay, and what I'm going to do in this case, I'm going to take up the log values. So I'm going to say log of probability, okay, so this is going to be probability, which is pi, okay, which we got like 0.9, 0.4 and so on, into my yi. Basically this is my original output what we had. Now this is first thing, plus 1 minus yi. So in between both of them, only one of them is going to be true. So if the value is 1, then this value will become 0, right? So only this term will make sense. And then log of 1 minus pi, which is again the probability, okay? And this. Let's once you go through this full formula, you will get a good insight that how this whole thing works. Now, as I said, with this part, this is for a binary classification, very specific to our old data, which I have presented to you here. So if you look at it, we do have the knowledge of yi, we do have the knowledge of our probability part like pi. So with this, we're gonna place our data to this. Now, if I look at this y is equal to 1, right? So if I have to place this data into my formula, so since I have a minus symbol, I can maybe put my minus inside and let's start solving it up. So my first value will become what? Minus log of pi. Pi is what? 0.9, right? So first row, I have the probability of 0.9 into yi. Yi is what? 1. So I got this value. Now, what about this part? 1 minus yi. So since the value is 1, so 1 minus 1 will become 0. So this term will become anyway 0. So it doesn't matter what is going to come out here. It's always going to be 0. So I got the first term for the first row as minus. So I'm going to note it down here. So minus log of uh, basically I'm going to get minus log of 0.9. This is for the first row. Let's calculate it for the second row also. And if you do calculate again, this is for yi as 1. So my 1 minus yi will become 0. And if you look at it, I will get minus log of 0.6. This is for the second row. For the third row, let's go back. This is for yi as 0 and yi dash is 0.1, right? So again, let me go back and plug in into this formula. And if I have to plug into this formula again, it's gonna become, so I'm kind of ignoring 1 minus n term, which I can always include at any moment. This is just for an understanding. I'm trying to explain what is log loss. Now after this, if I plug into this formula for the third row, so definitely this term, because yi is 0, will become 0. So only this will be kind of relevant right now. So 1 minus 0 will become 1. So 1 into log of, again log of. Now this is 1 minus pi, and pi is 0.1 for this. So it's become 0.9. Okay. So this is what the value we're going to get for the third row. Let's go back and place it here. Minus log of 0.9. And same way, if you compute it for the last row, I will get minus log of 0.6. If you do compute these values, I have done it already, so you need not worry about that. So if you do compute all this value, your values for minus log of 0.9 is going to be 0.0457, if I'm not wrong. This is going to be 0.22, and this is going to be 0.0457, and the last one again is going to be 0.22. Now let's look at the interesting point here. If my probability is 0.9, which is kind of high for value prediction to be 1, means if you get like probability of 0.9, and if I'm predicting okay this is going to be 1, that means it's a good prediction. My probability is kind of coming quite good. But if my probability comes out to be 0.55 and I'm predicting it to 1, there was still a dilemma. It could have landed to 0 even position, right? Because it could have kind of gone lesser than 0.5 and we could have gone to 0. But being this, basically this is very close to my 1 and it's a very good prediction for this row. So can you notice that this value comes out to be very low for this? If my prediction is quite good, my log loss value is going to be low, because as I told you, my log loss should be as minimal as possible. Now, if this is the second part, can you see this 0.6 probability? Here, this value came out to be high. So when there was a dilemma, my log loss is going to penalize me. It's going to say that, okay, this value is huge, so I'm going to give you the value of 0.22, which is high. Similarly, look at for 0.1. This should give you a low log loss value. Why? Because again, this is very good probability for my zeroth value. So you can notice this. I got 0.04, which is a quite low value. But for 0.4 to prediction 0, it should again return me a little high value. This is the whole idea behind log loss. So the main idea here is that more your prediction is better, the log loss value is going to be low. If your prediction is going to be kind of ambiguous, it's not that great, then your log loss is going to penalize you. So we want to keep this whole value to be lower. That's what is the whole idea behind this log loss. You can think about it. Let's say I have this probability as 1 instead of 0.9. Then in that case, what I will get? Log of 1, right? And log of 1 is what? 0. If I get log of 1 as 0, that means my log loss becomes 0, right? So if my probability somehow goes to exact 100%, that means I will get my log loss as 0 value. So this is the beauty behind this. Now I can extend the same thing to my multi-class classification example as well. So right now we understood from the binary classification part, but I can extend it to completely multi-class classification. So let's go and try to put the same thing into my multi-class classification. So for my multi-class log loss, the scenario is that I'm going to say 1 minus n. I'm going to run it again for all the rows, but this time I'm going to put it for my classes basically from 1 to C. And here I'm going to put yij, which means that it's going to be 1 if my xi, so it's going to be equivalent to value 1 if my xi belongs to class j, right? So if this is the part, it's going to be 1, otherwise it's going to be 0. Again, just go back again to the same binary classification. If you want, you can just change this value of C to 2 and I give this as a homework activity. It will just end up to the same solution what we have just gone through. I would suggest you to do that. Now after that, we can just say log of Pij, which again is the probability term that xi belongs to class j. Okay, that's a probability what we have. Now this is the formula which we can put it if we are talking with respect to our multi-class. Now, if we come back to our case study, we are talking about multi-class. We are not talking about single class. We are talking about multi-class problem. So let's understand that how in our multi-class scenario, how this is going to fit in for our project. Now, again, as I said, this is basically telling me that yi belongs to class J. So if you think about it, let's say in my project, we do have 9 classes, right? So let's say there are 9 classes. Now in this 9 classes, let's say I have this value as 0, 0, this is 1, and again all the value as 0. So this is, let's say, y for ith row of first classification. Again, this is y ith row second classification, yi3, right? So which is for ith row third, this class third. So let's say this is belonging to 3. So in this case, we can say that this value is going to be 1 for ith row where it's belong to class 3. So that's how we kind of represent it. Now, in terms of probability, if we look at, in terms of probability, if we go and kind of understand this, I have a data set, I'm passing it to my model, and I will get some probabilities. So my probabilities will look like this. I will have, let's say for first row, if I'm talking about, okay. So I do have, let's say first row, and this belongs to class 1. This is the probability for it. Probability that first row belongs to class 2. Again, you can keep on doing it till class 9, right? Because we have 9 classes. Now, think about it. Just put this in this way. Let's say I got a probability that for class 3, the value is 1. Okay. For remaining, it is 0. So what I'm saying that maybe I am getting a probability that for 1, 2, 3 till 9. So if you look at it for remaining output, because some of the probability should be 1. So what I'm saying is that let's say we come to a situation where I got an output from my model from when we passed this. We got an output that probability comes out to be 1 here for this. Now in this case, if you will calculate the log loss, you can just go back to a formula and put it. You will get basically log of 1, which is going to be 0. So I will get the log loss to be 0 in this particular row. For this row, I will get the log loss as 0, which is quite good. But in case, let's say this is 0.9, okay, instead of this, let's say this is 0.9 and I got this as 0.1 and remaining as 0. Now in this case, my log loss is going to penalize me. This 0.9 will return me a very lower value, as we have seen it in the binary classification as well. But at the same time, this is definitely going to give me some value greater than 0, right? So my log loss will have some value. So the best model for log loss definitely should be 0. The value for log loss is 0. That means I'm creating a perfect model. But in real world, we never have a perfect model. So in this case, the model can lie from 0 to infinity. So we will see that how to use it and how to build the model with the log loss keeping in mind. But this is what log loss is all about. So we just understood what is log loss. We will see to the next lectures that how to use it. Okay, so in the last lecture we understood about what is the log loss. Now we have a bigger problem here. Problem is that let's say if I have a metric of accuracy. Now in accuracy we know that my accuracy, if it is like uh, can be between 0 to 1, and in 0 to 1 case, if more closer to 1 is good, right? So it means that if it is, let's say, 0.90, then we say that we have a 90% accuracy in this case. So it is closer to 1, it's good to this. Similarly, we do have AUC, area under curve, and this value also, if it is closer to 1, it's good. Now we do have a lot of metrics where we do have a defined criteria. If it is falling in this, it's good, or if it's not coming to this is bad. But if you look at the log loss, in log loss, the value can go from 0 to infinity. Now the thing is that, yeah, I know that if the value comes out to be somehow 0, it's a best model, right? It's a best model. There's no doubt about it. But the problem is that we do not generally get as a best model, right? Maybe let's say if in some model I use and I got the value of 1.5. Now, what I can really say from this number? Can I say that the model is good or bad? How can I really do some comparison? Because the highest value can go to infinity here, right? So there should be some kind of comparison metric to it. That's the reason log loss is not that good in visualizing and giving you the output. So now in our problem statement, since we have to use log loss, so how we should really go about it, how we should really think about using this log loss matrix and say that, okay, this is a good model or a bad model. Now, one way, or there can be various methods. I'm going to tell you one method. One way is, how about if we generate a random model? When I say random model, I'm talking about a model which is the worst model possible. Okay, this is the worst model, which will be which we will create by completely by some random numbers, and that model is for that model which we're gonna generate on our data set. We gonna basically compute the log loss. Okay, let's say that log loss come out to be 3. Let's say that log out comes out to be 3. Then after that, what we will do, we will start generating our models. Okay, let's say we will generate LR model, okay, which is logistic regression model. If this LR model is going to return me, let's say, log loss of, let's say, 1, right, or 1.5, in that case, if I compare with 1.5 with 3, definitely LR model is performing better than my random model. That means this model is better in comparison to any worst model which we have. So this is the strategy which we're gonna take in order to deal with this log loss. And maybe we will compare this basically log loss for various algorithms, and we will see that which algorithm is going to give me the minimum log loss, because that would be our main focus here. Now, in order to do that, how we should generate a random model? Now here we are working with probabilities, right? So in terms of probabilities, if we look at, definitely all the probabilities of, let's say, 1, 2, 3 till ninth model, if sorry, till ninth model. So here the sum of these probabilities should be equivalent to 1. So the way I will generate this model is, random model would be that in the end, the final probabilities which I will randomly generate is the sum of those probabilities should be equivalent to 1. That's something which we have to keep in mind while creating it. So let's go and see how we can work out on this sort of models. So first of all, we need to work on all the probabilities for my test data set and my cross validation. So we are taking the length for it, because for each row we gonna generate this probability, right? For first row we gonna generate the probability for all these 9 classes. For second row also we gonna do the same, and similar thing we gonna do till nth row. So that's the reason we got for this, because we want to generate the log loss for my cross validation data set as well as for my testing data set. So that is something we gonna do now. Now, first what we did, we kept everything, because we need for all the 9 values, right? So we need to fill up basically 9 values here, 1, 2, 3, 4 till 9. So that's the reason initially we took all the values to 0, all the 9 values to 0, and later we're gonna fill it with some more appropriate values. Now, in order to do that, what we're gonna do, we're gonna run it for my whole cross-validation dataset, and we're gonna do the same thing for testing later. First, we started with cross-validation dataset, and we started putting the value randomly. Now you may say that, okay, randomly this may not sum up to 1. That we will do in the next step. So we put the value randomly, and in the next step, to make the sum value basically equivalent to the part, what we did, we basically divided it with the sum of all those part, and this is gonna ensure that the sum of the probability should be equivalent to 1, right? So that's what we're gonna get. Now after this, once we got this part, we have to calculate now the log loss for this cross validation in the random model. So what we will do, there is a function called as log underscore loss for calculating all this for us, and here we're gonna pass our actual output, which is for cross validation, and my predicted part which we just computed here, which is random probabilities which we have just put in, so that the sum of all these probabilities should be equivalent to 1. And once we pass this, we got the log loss to be 2.49 for cross validation. Now what does this tells us? This tells us that 2.49 is the worst log loss, and if any of my model which I'm gonna generate is gonna be greater than this, that means it's a worst model, means even it worse than worst model, and we should not consider that. So we got some sort of criteria now that all the models we gonna generate should have lesser than 2.49 cross validation log loss error. Let's do the same thing for my basically for my test also. You can see that we are taking exactly the same route for this. We took all the 9 values to 0 initially, then we took the run it for all the test data rows, and we put randomly 9 values, and we made sure that all the values should sum up to 1 probability values, and we are passing my y-test original value and the predicted, which we have just done it randomly, and we got the log loss of 2.48. So for the random data model, for my test set and the cross validation set, we are getting the log loss of 2.48 and 2.49, which is quite close. So this is how we got this part. Now, this is basically for the random model, right? So we do want to do some more analysis on this. So what we gonna do is, we definitely, if you look at it, let's say if my random model is returning this sort of output, let's say 0 0.1, 0 0.1, 0 0.05, 0 0.05, and so on, in such a way that then the last probability is 0.2, right? So let's say this is my output, and all this sum of 9 values is equivalent to 1 somehow. Now, in this case, let's say if 0.02 is the highest value, so this should return, right? This should get returned that when class 9 is having the highest probability, so it should return it. So that's what we are doing with the argmax. So we are going to now get the index at which it is highest. So you can see that we gonna get it in my predicted underscore y, and these are all the indexes, but you can notice that it have taken the index from 0 to basically values 0 to 8. So we have to increase it to bring it to the scale of 1 to 9. Let's add it plus 1 to it so that we can bring it to the same scale in which we are solving our algorithm. So this is the way we have generated our random model. We got our log loss for it, and now we gonna work further on it on the same random model to look at various metrics, because once we get this, we definitely want to ensure that how my confusion matrix looks like, how my precision matrix looks like, how my recall matrix looks like. So this we will do all those things in the next lecture. So after we got our random model, which we have just seen, now let's see that how good that model was. Definitely the model cannot be good. And we have seen the log loss was also high. But now let's see that if we calculate something like confusion matrix, which will return you the accuracy, or if you go for precision and recall, how it will look like for random model. But do not expect a good output here, because definitely it's a random model. Now, the code is very simple for it. We are going to calculate this matrix by using this confusion underscore matrix function. And in this function, we are passing our original data set and my prediction. So prediction, we got it from here, right? So we got our predictions here by getting those indexes. Now, once we got it, I'm gonna just plot this heat map matrix. It's quite simple code, which you might have seen in a machine learning algorithm. So my label is from 1 to 9, and we're gonna put our matrix C to it, and let's see that what's the output comes out to be. Now this is my output, so you can see that it's a 9 cross 9 output, and your basically this axis, y axis, includes your original class, and this part is your predicted class. So if you look at this, definitely I do have some coloring code here, that if the value is going to be kind of higher, then it's going to be blue color, otherwise yellow color. So I want my diagonal element to be always high, right? So that's the main thing basically which I look at, because what does this diagonal element tell us? It means that there are 10 values which, if you look at this part, this means that there are 10 values which are actually belonging to class 1, and they in the original class also they belong to class 1, so they are 10 in number. And similarly you can look at the other part, and you can see with this that it's do not look that great. So all these values here and here are errors, right, where we my prediction have not definitely happened correctly. So this is my accuracy. So you might be seeing your accuracy confusion matrix a lot while you were solving your normal small case studies when you're solving your machine learning courses, but here this is going to be a little huge because my it's a multi-class classification problem. Now let's go ahead and see few further things. So we are now going to look at precision and recall. So we just understood that how the accuracy is being looked at, but now we're going to look at precision and recall, that what exactly this number is going to come out to be. So my precision is another matrix where we computed again the matrix B, and we are going to calculate this precision matrix. Now, what does this precision matrix basically tells about this? Though I am pretty sure that you all might already be aware of precision matrix and recall matrix, but again, just let's try to intuitively understand this particular portion. Now, in this case, when I see this value of this 0.139, it means I'm talking about 13.9%. What this value tells us? This value tells us that of all the points predicted to class 1, 13.9% of the class actually belongs to class 1, right? Or so if you look at it, basically the way precision is calculated is, if I look at this particular point, so this point divided by all these points, okay? So this is how we calculate it. Or if I talk about this point divided by all these values, all sum of all these values, okay? So, or if I talk about this point, how this we got, so from the, and this is all done on the confusion matrix. So on confusion matrix, whatever the entry is coming here divided by all the sum of all these points, so this is gonna return you again your output in terms of percentages. So we always look at it in terms of percentage. So let's say if I have to talk about this means that 11.1%, right? So it means that of all the points which is predicted in your class 1, okay, 11.1% actually belongs to class 6. Okay, this is what basically it means. Now let's go and look at your recall. Again, this is very similar to this, but only difference is on the confusion matrix, again on the values what you're getting. So let's say if I have to calculate the recall on this data point, so this value divided by sum of all these values, like this. So it's just it's a row wise thing which happens, and when we were talking about precision, it was column wise division. So now if I go back and again look at this, my recall values, so we got basically these values as again the same explanation, like if I have to look at this point, so divided by sum of all these points on your confusion matrix. So that's how we calculate it. Now, how we can infer this? In order to infer this value, again, we look at something like this. If let's say if I am talking about this part, it means only 8.8%, which means of all the points which actually belongs to class 1, only 8.8% were predicted to be in the class 1, right? So that's how you look at a recall, and you can see that all these three matrices are coming out to be really bad. Okay, we will now start doing the comparison in the other way as well. Thank you. So by now we have computed uh, how to calculate the confusion matrix, look at the accuracy for it. We have seen that how to work with respect to your precision and recall, and now we gonna take one further step, and now we're gonna play with the columns. What I mean by that, so if you remember from my original data set, we do have three independent columns and one dependent column. So one column is gene, second column is variation, third column is text, which is your research paper text, and the fourth column was your class, which was your dependent column. Now this class value was falling from 0 to 9. Now what we are going to do is we would like to understand that how impactful this gene is for the class. Means, is gene is really important independent column if we compare with if we have to predict the class variable. So that's what we gonna figure out first. So in order to do this, we will do some analysis, and also if it is relevant, in order to identify that as well, we need to bring this categorical variable into an appropriate format which my machine learning algorithm can really understand. So right now this is completely categorical, so my machine learning algorithm cannot take that value exactly as it is. So we need to apply some sort of techniques to get this done. Now, in order to do that, let's start with some analysis here. Now, the first thing is we would like to see that how the distribution of this data looks like for gene column, and we can see here that we do have like all these values like BRCA1 is occurring 174 times, TP53 is occurring 102, and the unique genes are like 227. Now we want to maybe plot few things to get even more better understanding about this data. So what we are doing, we are plotting a cumulative distribution plot, and if you look at this plot, what this tells me is that if I look at the top 50 values, they are contributing to almost 75% of your data, right? So almost 75% are being covered by top 50 genes itself, and remaining values may be kind of less occurring. So this is one of the analysis which we can make out from this particular part. Now, as I was telling, that the first thing before we even think about building any machine learning model is that we need to convert it into an appropriate format so that my machine learning algorithm will be able to take it as an input. So as we already know from machine learning techniques, that there are two different techniques to do that. One is your one hot encoding, and second is your response encoding. I'm really surprised to hear this, that a lot of machine learning engineers are not even aware of response encoding properly, and it's a very powerful technique. In fact, we're gonna see that in which all algorithm response encoding works best, and in which all algorithm one hot encoding works best. So there are various cases where maybe my response encoding will perform much better than one hot encoding. In fact, people who are already aware of one hot encoding, they might be aware that one hot encoding do creates a lot of columns for us. So since it do create a lot of various column for us, at some time creates a problem. Just to give you an example that how one hot encoding work. So let's say I have a column which belongs to, let's say, country. Okay, and in this country column we do have some data points, let's say US, India, maybe we do have something called as Sri Lanka, right? So we have, let's say, these three countries. Now the thing is, if I have some more columns, maybe they are numeric or non-numeric, doesn't matter. But if I have to feed this numeric data to my mathematical function of machine learning, it is not feasible. So how to deal with this? So one way could be that we can just say that, okay, this is US. I'm gonna give a numeric value 1 to it, give a numeric value 2 to it, and give the numeric value 3 to it. Now this solves the problem that, okay, we have converted our categorical to numeric, but this brings another problem for us. The another problem which will come here would be that if in this particular case we are giving some number, so now it is sounding like India is greater than US or Sri Lanka is greater than India, because as soon as you give some number, it start working like an ordinal data. Now this is where again the problem starts. So how one hot encoder fix it? So what one hot encoder instead do is, so let's say it looks at unique values present in this column. Let's say there are three unique values. Maybe after that, India is going to repeat into this data and so on. So what it do is, it's gonna remove this particular column. It says that let's remove this column, and instead of that, maybe add three unique columns here. One belongs to US, second belongs to India, third belongs to Sri Lanka. Now in the first row, since I have US, I will give 1 0 0. I have India in the second row, so I will give 0 1 0, means whichever entry is there, give the 1 to it, and remaining values give 0 to it. Similarly, I do have Sri Lanka. Now here I will give 0 0 1, and I do have India again, so I will give 0 1 0. This is how we can represent it. Then after that, we do also one more step as a machine learning engineer, usually, that if I do know the value of US and India, I can definitely tell the value of Sri Lanka. So maybe I don't need all the three columns, and we remove one columns from it depending on whatever we want. So that's something what we do as a one hot encoder. So this was a very quick review of this. But if you look at the problem of one hot encoder, we are facing one issue here, that if your unique values are too high, let's say my unique values are, let's say, 1000. Now in that case, are you going to end up with 1000 new columns? means you are increasing the dimensionality of your data, and that too you will have so much of sparse data. This is a very big issue with respect to one hot encoder, and few algorithms have a big trouble with this, especially if you talk about like trees kind of thing, like random forest. So this is where maybe this will create problem if you have huge dimensionality data. Now, in order to solve this, we do have something called as response encoding. We also call it sometimes as mean imputation. Just like how we used to deal with the NA values, we start dealing the categorical values also in the same way. Now, this is an art. You need to learn it, that how to basically convert your values in a way that it should make some meaning out of it. Like in the previous example itself, where we have taken, let's say, three values of US, India, and Sri Lanka. Maybe finally we are trying to output something called as height here. Now, what we can do here is maybe we might want to replace all the mean value, mean height of US here. So I will replace this US with some other value. Okay. So the more thing which can make sense here would be that instead of keeping the US value, maybe I would like to replace it with the average height of all the people present in country US. Maybe let's say it comes out to be 160. For India, let's replace it maybe the average height of all the Indian people, so 152. So I do need to have maybe sometime domain knowledge to do it, or it depends. So right, so we can basically take up this call and can replace with this. Now this is called as response encoding. Now in our problem statement, if I go back to our problem statement, where we do have to look at genes, and from those genes we are going to replace our data. So how we gonna do that, right? So that's basically is a question for us, that how we pull up the response encoding here. Because here we cannot replace with the height or weight or something like that. So what we can do, so let's imagine I do have a data of this sort. So let's say I have two columns. One is gene and second is, let's say, class. Now let's say I do have a value called as gene I. So let's say I do have all these gene I value here, and I have corresponding classes to it. Let's say 2, 2, 2, and I do have, let's say, 3, and there are some more, let's say 3, 3, 3, and I do have this gene value even going up here. So now in this case, let's assume that this is all 100 values. Okay, let's say we have this 100 values. So it's saying that this gene is there, so it's belong to class 2. This gene is there, so it belongs to class 3, and so on. So now here basically, let's say these values are, let's say, 30. So let's say this values are 30, and let's say these three value, class 3 is, let's say, 70 out of it. Okay, so these are, let's say, 70. So how we basically can work on it? So in response encoding, instead of creating like depending on the unique values, we are creating various column. What we will do, we will say that for every row we will create 9 columns. Okay, so like this is one row, right? So this is one row. So for this row I will create 9 columns. So now I will add, let's say, all these 9 rows. So this is, let's say, 1, 2, 3, 4, 5, and this is 9. Now what we're gonna do further to this, now if you look at this probability term here, what we are basically going to do is, we this is probability 3, right? So we can also call it as probability that y belongs to class 3 given my gene gi. Okay, this is what I can basically say about it. Now if you look at this, this is going to be what, 0.7, because this is, if you can recall from your Bayes theorem, what is this value? This value is saying that I want the probability that y is equal to 3, and probability of gene I divided by probability of gene I, right? So this is going to be 70 divided by 100, which is total number. So I'm going to get 0.7. Similarly here also I will get 0.3, and in the remaining place I will put 0. So this is how we will be imputing the value instead of keeping the categorical. So now in the first row, I got, let's say, this value as 2. So in that case, we will be basically replacing accordingly to whatever my computation is going to come for it, right? So for every value, we're going to replace it with respect to my 9 columns here. Instead of keeping it 1, That's the whole intention of using this. So in this response encoding, definitely we're gonna have only uh, basically, if you will look at it, we're gonna have only 9 columns instead of having like multiple columns being available to us. So that's the advantage of basically using this response encoding instead of basically using anything else. So this is quite interesting, and I'm gonna give you more insight about it, and once we do it practically, it will start making even more sense to you, because we can go ahead and start exploring with this data, and you will notice that at few algorithms it works really well. So we will learn all of those techniques as well. So after we understood what is one-hot encoding and response encoding, and we have also seen that how response encoding would make sense to this particular problem, where we will look at for a particular gene I, we will look at the probability that how it is occurring for that. So that is the value we're going to impute, and the advantage we have seen for response encoding is that it will create number of columns equivalent to total number of basically number of class outputs you have. So in this case it's going to be 9. Now we will see that how to perform these things in the practically in the Python notebook. So first thing is that we need to create a one hot encoder, and I will show you up that one hot encoder will create much more columns for gene in comparison to when we will go back to your basically response encoding part. So here we are going to take the help of count vectorizer, as you might already be aware of this, and we are going to pass my gene column in the fit transform, and this is going to convert it for my train, for test, and for cross validations. For all the 3 data sets we're gonna do the same, and after we got it, we can look for the train shape or test shape or Chevy shape, doesn't matter. But if you will look at it, you will notice that for the gene column it have created 227 columns, right? Which is huge. Just for one gene column we got 227, but it's okay. There are few algorithms like basically if you look at, let's say, linear logistic regressions, they perform really well if you have even huge dimensions. So we will see in those cases there will be no issue, but there will be few algorithms like KNN, where maybe, like for example, when I will say KNN, K nearest neighbor, then in that case maybe this may not work good, and we may want to move towards a smaller dimension data, which response encoding can help us do. So now let's go ahead and see a few more things to it. Now here you can see we can also look at all the column names that I have created. So we can just say get feature names, and it's going to return me all the column names which it is going to return. Now after that we're going to see how to perform a response encoding. Now for response encoding, what we are going to do, if you look at it again, we are passing this gene column, and here we are also going to use something called as Laplace smoothing. Now this is also one of the very interesting concept. In fact, this Laplace smoothing, I'm going to use this almost throughout this project, and even at a lot of places I'm going to use this calibrated classifier as well. So you should really know what is all this. If you don't know, don't worry, in the next lecture I will explain you what this Laplace smoothing is required, why Laplace smoothing is required, and basically what's the significance of this, why I'm basically using this into my project. Now in this case, I have chosen the value alpha for performing Laplace smoothing, but right now don't worry about it. As I said, I'm going to explain you what is Laplace smoothing just in the next lecture. So for now, just take it some value alpha, we are passing it on, and it's just getting it work. Now after that, what we are doing, we have created a function. Now what I have done for this function, this function is taking my input for Laplace smoothing, one something called as alpha, and it's taking the gene column which is there, and your training data set or testing data set or cross validation data set, and it's gonna return you the response encoding value for it. Now when this is gonna be returned, you can notice that when I looked at the shape of this, the output of this, you can notice that I got only 9 columns instead of 227 columns what we were getting in one hot encoder. That's basically is the beauty about this response encoding. Now for doing this, this function is not available to you by default. So for this I have written a Python code for it, and I would strongly recommend all of you to go through this particular code. This is a well commented code. You can see that each and every line is properly commented so that you should not face any issue in understanding this particular concept. So it's very simple code. Just go through it line by line, and this is exactly the same thing what I explained you, that how we calculate the response encoding in terms of those probability terms. So please go through it line by line. It will really help you to understand. So this is one also an art you should learn. Though definitely you need not be a very good Python developer, but this is quite simple to get that. So I leave this as a homework for you to basically go through this particular functions and kind of work on that. And Laplace, let's get, I'm going to introduce this in the next lecture, this Laplace, what is collaborator classifier. So I'm going to talk about all this in the next lecture. So now we understood that how to get the response encoding and the one hot encoder. So right now we have just converted the gene particular column to basically with respect to either a one hot encoder, which is going to create 227 columns, or with respect to your response encoding part, which was creating 9 columns with respect to your probabilities. So once we have got that, then the question is that how good is this gene column for my final output, right? Now, what is the way we can actually go and test that? So one nice method is, we have already created a random model, and there we have seen that what is my log loss, right? So we know my log loss was, let's say, 2.35. Let's say, I do not exactly recall, but it's, let's say, was 2.35. Now, in this case, what we will do, we will create a very simple, maybe logistic regression model, okay? And I'm going to build it assuming that I only do have something called as only one column with us, and that is called as gene, okay? And we are trying to predict from it my classes. So simple model which we're gonna create. And during this process, if my log loss comes out to be lesser, my log loss is going to be come out to be lesser in comparison to your random log loss, then in that case gene is a good feature, right? So that will be the way we can say that, okay, since it is performing better than any random model, so definitely gene is going to be a important part for my prediction. So that's what we are going to do. Now, in order to do that, we need to understand a few techniques, like basically we have to work on something called as Laplace smoothing. I will explain you what is this now. So this Laplace smoothing is a very interesting kind of method which you should be aware of. Now, this is the concept which you might be introduced in your machine learning concept in naive base, because that's where it have made more sense, but it's a very generic call. So in naive base, what you do, right? If you recall, you kind of, let's say you have various words, W1, W2, W3, and so on, till let's say WM, and you have your classes. Let's say the classes can be either 0 or 1. So in this case, we used to calculate during your training phase I'm talking about. So used to calculate the probability of W1 given that y is equal to 1, because in training phase I used to know my 1 value, that where is my class 1 for word W1. Similarly, I used to calculate for remaining things as well, and same thing we used to do it even with respect to your y is equal to 0, right? So this is the way we used to work in your naive Bayes theorem. Now, I'm not going into depth of all this, because again, I'm keeping my assumptions here that you know what is naive Bayes, okay? But if you really don't know, do not panic. Please go back and do a revision of this algorithm. Or if you still face any issue, guys, feel free to post your questions on your discussion forum, and I would be more than glad to create a video for it. Okay, so if you really feel, or if you want that I should create some nice video for with a mathematical intuition for Bayes theorem, definitely I will do that. Now, coming back to this. Now, there is a problem is, this is happening in the training phase. Now, all this W1, W2 till WM, what I have is are the words present in my training data. Now, if I go back and let's say if I look at my query point, which is my test query point, And let's say by any chance my I have, let's say in my this part I have this, but I do have a word w dash, okay, which is not a part of my training set. Okay, this is quite possible because English keyword is huge, right? So there is a possibility that in my training data I do have some word, but the same word in the test data, or maybe I have a test data set where I do have word which is not even present in my training data. So I have no idea about this w dash, that how it's gonna behave. What is the probability I need to keep for it? So now the problem is, if I have to, let's say, get the probability that what is the probability that it's going to be 1, given that it belongs to my test queue. Okay, now this test queue is nothing but my y is equal to 1, and this is going to be like w1 w2 till w dash, right? Now there's a problem is, if I break down this probability as per Bayes theorem, it's going to break down something like this: probability of W1 y given 1. This is going to come from a training set, and it's gonna go on. But in the last, I will have probability of W dash y is equal to 1. Now the problem is, I have no idea what to do with this term. Now one way could be, you could say that, oh, how about drop it? How about ignore it, right, and take the remaining term? But if you are dropping it, don't you think it is equivalent to saying that you are equating the value to 1 to it, right? And that is not the case. You are giving the value 1 to it if you are actually going to do that. Now there is another idea what people can say: how about making it 0? But if you make it 0, then the whole multiplication will go 0. So again, that will be a problem. So in order to solve this particular problem, we use something called as Laplace. Now, what is this Laplace smoothing? Or sometimes you will hear this term called as additive smoothing also. So that is also, sometimes people do refer it like that. So now in this case, what we do, so we will say P of W dash means probability of W dash where given that y is equal to 1. This is going to be equivalent to earlier what was happening. If I have decided that if I would have gone with the technique that, okay, number of training points, basically that it belongs to y is equal to 1, that was basically 0 because there was no points present in my training part, or divided by total number of values. Let's call this as n1. So in the earlier case, we were deciding it to give the probability 0, which was not working good for us because 0 will multiply with everything and return 0. So in order to solve this problem, what we will do, we will add a alpha term to it. Now alpha will be a hyperparameter. Okay, so this alpha and alpha k. So you might be using all these hyperparameters a lot in your machine learning. So this k is nothing but your total number of classes. Okay, so like in my last example, I have taken y as value 0 or 1. So in this case, my value of k could be 2. So in this case, my value will become alpha n1 plus 2 of alpha. Okay, like this. Now typically we take the value of alpha as 1. Generally we do that. So we generally want to keep it a reasonable value, and definitely it is a hyperparameter. So you can always change it and see that where your model is giving you the best output, and you can stop there. That's something is always in your hand. Now let's say I have taken the value of alpha as this and assume that I do have 100 points. So my n1 is 100. So what's going to happen in this case? My alpha value is 1 and my this is 100. So plus 2 into 1. So what I got, 1 divided by 102. Now, if you look at this value is definitely not 0, right? This is going to be a small number, but it's not 0. Now, you take another case where, let's say I have gone for alpha value to be 10,000, right? Or some huge number. Now, in that case, if I go back to my same part, so 0 plus 10,000 divided by 100 plus 2 into 10,000, because if you remember the k was 2. So here we will get something like 10,000 divided by 210. So I will get somewhere roughly by 1 by 2, not exactly 1 by 2, but almost 1 by 2. So you can see that if I control this value, it can also help me in kind of controlling my something between bias and variance, right? It's a very interesting part. You can actually play with this and see to this part. So this really helps us in kind of doing it. Now the question is that, are we going to only do this alpha multiplication, basically this alpha part, only with respect to my data which is not present? No, because we can't really filter out all this. So what we do, we do this Laplace smoothing for all my whole data set. So even if my data is present, so let's say I have some probability coming out to be 2 divided by 100. Maybe that's the case. It's not 0, but it's 2. So in that case also I can say alpha plus alpha k. It's not going to make any difference for you. So even if the value is there or not there, doesn't matter. We're going to add this for every term present into my algorithm, and that's what we're going to do. So I hope now you got an idea that when we were doing this response encoding, I was considering that alpha is 1, and then I was passing it. So I was just ensuring that if some place it's not present, then it should not return me some value like 0. So that was the idea. So again, this Laplace smoothing is a very interesting concept. Similarly, there is another thing which we also going to use, called as collaborated classifier. So let me explain you what is that. Calibrated classifier. So I'm explaining you all this because I'm going to use this while building my model. So this is a very simple concept. Let's say I have an input xi and I'm passing it to my model m, and I got the value yi. Now this yi may not be mandatorily a probability term, right? So it may not be probability. Now, in that case, maybe we need some output in terms of probability. For example, like when your final output is required in terms of log loss. Now, in this case, log loss definitely needs probability. Log loss is a complete concept on probability theory. So now, in this case, what we should do then? So what we do is we build it again with a classifier, which is called as calibrated classifier. It may be a sigmoid function, or it may be any advanced level function like isotonic. Okay, so then it is going to return you the form of y dash. This is going to be probability. So as a thumb rule, you can think of it that whenever you're going to use log loss, it's always a good idea to use calibrated classifier, so that your final output should always be in the probability format. So it's going to help you to convert it to the probability format and use it. The third thing we're going to use is SGD. I believe this everybody is already aware. It's called a stochastic gradient descent. Okay, this is, we use it for optimization purposes and all. So this I hope everybody is clear, right? So so these are things which you need to know for understanding the further machine learning model. And now as a next step, we gonna basically approach the whole problem from these three perspective a lot. Okay, so as we discussed last time, now we're gonna create a model considering only my gene column. And in this particular case, I'm gonna create a logistic regression with respect to my SGD classifier. So I'm gonna use the basically SGD classifier to do that. And at the same time, I'm also going to use my calibrated classifier, which I explained you in the last lecture, and we will be doing the Laplace smoothing if required. So let's go ahead. So here you can see here that I'm going to use one of my alpha parameter. Again, that regularization hyperparameters are required in SGD classifier. I'm also going to use L2 classifier in this case. So you can see that basically I'm going to use this L2 as penalty. I'm not using L1 norm, which is basically, so I'm going to with the L2 distance calculation and all. And I'm going to use this is loss is log, which means that I'm going to use logistic regression. But you can notice that this part I'm using it as a hyperparameter. So I'm going to run this algorithm for various value of this alpha, and whichever alpha is going to give me the best result, I'm going to just take that up as a final result, right? Now here what I'm doing is I'm computing, I'm basically doing this fit part, and you can notice that I'm using one hot encoding. So the way it works is that if I go back and understand this point, so if I go to one hot encoding, even if you have, let's say, huge dimensions, even in that case, your logistic regression, LRSVM, these kind of models works really well. And similarly, if I go for your response encoding, so response encoding, you have like naive Bayes, random forest, okay, or basically these, or KNN, I can also put KNN to it. So in these cases it works. Even knife based you can use it for one hot encoding, that's not a big problem. But yeah, for random forest and KNN definitely you have to go for a response encoding. So that's where we do it. So since we are going to use here logistic regression, I'm going with one hot encoder. But I would leave this as a homework exercise for you, that you can play with other models with only gene and see that how your log loss comes out to be. And you can notice that I'm using something called as calibrated class of classifier here. And if you look at this, what basically we are passing to it, we are passing this model, and we are using the sigmoid function just to ensure that we return everything in the probability format. And once we have got that, we are taking our one hot encoding data and basically going to train this model, and after that we are going to predict, and in the last we are going to use log loss, right? So that's what we have done. Now let's analyze this output which we are going to get. So here you can see that we got the value of for various alpha, like we have taken one alpha as 10 to the power minus 5 and this and so on, and we got for every different alpha we got basically different basically log loss. And if you look at it, this log loss seems to be minimal, which is coming from 0.001, right? So that's what basically we are getting the minimal log loss. So we can choose this alpha and go ahead with this. So what we're going to do further, we can also plot a graph and see that which is giving me minimal. You can see that when alpha was near to 0.001, maybe that's where it's going minimal. And even after that, what we can do is we have just computed this, but now we need to also choose the same alpha and go ahead and calculate for my testing loss. We will also do it for the cross validation loss also, just to have our comparison ready whether the model is overfitting or not. So let's do that. So what we are going to do to achieve this, we are going to now we have already got 0.01, which is going to be stored in best alpha, and after that we are using the same L2 Lagrange logistic regression. Everything is good. Created a model, we fitted this, everything is all good. We are using calibrated classifier, and in the last we are creating the log loss for each, right? So we are going to do a log loss for test, for cross validation and so on, and this is the value which we are getting for each part. So for with only gene column with a one hot encoder, logistic regression plus calibrated classifier and so on, we got our log loss value to be this. And if you look at this, this is very less in comparison to what my random model was giving us. So that's a very good insight what we're getting here, right? So this is telling me up that my model is good, not that bad, right? So which means that with gene column it's definitely having a good impact, because this is much lower value in comparison to my random model. Now one more thing which we also want to look at a lot of the time, that how stable is my model. Now when I say stability, what I mean by that, now you have gene, and since it's a random distribution, there is a possibility that maybe you have genes basically which are here in the training set, and only very few are coming in my testing set. So this is, let's say, my test set, and this is my train set, and let's assume we do also have a cross validation set. So if this overlap is low, okay, so because there's a possibility that maybe in the gene some gene value which is there in train set but not there in the cross validation set, right? So that's a possibility, so that's not going to overlap. So we definitely want to ensure that I do have a good overlap. So more the overlap, better it is. We definitely want to make sure that if I'm training something on some gene data, that should be present in my cross validation. It should not happen something like the case where I talked about Laplace smoothing, right? So that sort of thing should not happen, that in the test data something comes up but I have not even done any training on it. So though we have the solutions for it in terms of Laplace smoothing, but it's not still a great idea. So we do want to have the very less part. So if the more overlapping it is, that means the data is quite stable. My model is also going to be stable. So that's what we are going to look at here. So you can see it in this case, it's telling me that my testing data, if I have 665 points, 639 are common in my train set and my test set, which is good. Because if I look at the percentage, I have almost 96%. Similarly, in cross validation also, with the train set, if I compare, we do have 96.42 points which are overlapping, which is good. So looks like my gene column is going to be quite well. In this case, it's going to be good overlapping, so it's going to be stable. And even my log loss is good, so gene column is definitely important for my classes in this case. Let's follow the same steps on my variation column. So we have just seen that the gene column was relevant. Now we're going to work on the variation column and see that whether my variation column is going to be relevant here also or not. So in order to do that, again, we are going to look at that how this distribution looks like. So we can notice that we do have some 1936 unique values, and the distribution looks like this, that we do have training mutation, this, but if you look at it, apart from these four values, almost the remaining values have the values occurring less than 5 in number, right? So maybe we can see the same thing during when we are going to build our basically graphs as well. So let's see whether that is happening or not. So let's go down and see this part. And yes, we are right. So you can see that there's a spike here. But after that, the values are moving like this. But in fact, if you look at it here, 80% of the data may be falling till 1500, right? So because the distribution for the remaining points are very less, maybe they are just talking less than 4, 5, this number, right? So that's what is happening here. Now let's go ahead and see a few more things. Now for this portion also, we're gonna create the one hot encoder and response encoding. So for this, when we did the one hot encoder for my basically all the data set, which includes my training data, testing data, and cross validation data, and when we created this, we got 1967 column. You can see that it's huge, right? Now then after that, I'm gonna again apply my response encoding, and again I'm gonna call the same function which we have created above, and this is gonna return me only 9 particular columns for my variation. So I hope now I no need to explain in detail about what is happening here. Then after that, we're gonna build our model in the same way, just keeping my variation column. And again, the same technique, I'm gonna use one hot encoder, I'm gonna use SGD classifier, same L2 penalty, same logistic regression. I'm gonna run it for a different value of alpha, and when I'm going to run it, I'm gonna get this output. Again, I will look at the minimum value out of it. We will do a plotting of this part, and once we do the plotting, we will get the best alpha, and we will start generating the log loss for each. Now let's look at the log loss. If you look at the log loss, for my best value of alpha, my log loss for test, which is more important for me, is around 1.70, which is again lesser if I compare with respect to my random model. So definitely it is a good model. It's a good feature to look at. It's not a bad feature. So we may want to even look at this feature and will not ignore it. So this is also one way to look at if any of your column is important for the final output. But if I look at the stability point of view, then my percentage have gone down. So my test data have only 10.97% of overriding here. And for my cross validation, I do have 11.4% of this. So this is a problem, right? So if you look at it, definitely this is low. So looks like this feature is not very stable, but at the same time, since my log loss is pretty low, if it would have been kind of nearby to my basically or exactly kind of nearby to somewhere random model, I would have kind of ignored this particular column. I would have not considered it my final model which we are going to create. But in this case, maybe we are okay to kind of ignore that, because definitely if we look at this particular scenario, we though we have a less stable feature in terms of very less overlap is happening, but let's give priority to log loss and decide to keep this column for our case. So this is how you can look at this. Now after that, we have to look at text column. We will do that in the next lecture. Okay, so now let's work on the text data. So for working on text data, because text is going to be very huge in comparison to your gene or variation, so in this case, we have to deal with it in a different way. So we have created few functions for it. So like first function we have created to just get the count of each word, like how many times each word have occurred in this particular scenario. That is what we're going to take as the first step. Second function we have got for getting the response encoding. Now for text data, how we will perform this basically this response encoding, that's a question, because it's going to be huge for us. So let's talk about it. So again, we do have values from 1, 2, 3, and so on till 9. So this is my value. Now, if I have to get the probability that the value is 1 given your text, this is how we work in the naive base, right? Now, in this case, if I look at the basically the output for it, it is the value is going to be proportional to my value from 1 to k, and we will say probability of y is equal to 1 given basically your wi, right? So that's what we gonna have here. Now, so this is what we want to compute in this case, right? Now, this value can sometime can be very low also. This can be very small. So in order to handle that, we can take the log. So after we take the log, this product will get converted to the sum format. So this is going to look something like this. I'm going to take the log on both the side. So log of probability that y belongs to 1 given the text data, right? So, and because here we go with a naive assumption that everything is independent, so that's the reason we do that product. So this is going to be not equal to but directly proportional to, again this is gonna become like sum of this, because now when we take a log, this is gonna be sum, then log of probability is equal to 1 uh, given this word, right? So basically given words whatever we do have. So that's how we can do it. And then once we calculate this up, again we can take an exponent to get back the value in the appropriate format. So all these things we can anytime do. So again, it looks very similar, there's nothing strange, but just want to show you that this function is doing. You can see that here also we are computing the log, right? So that's for the same reason what we are doing it, and after that you can see that we are doing the exponent also. Once we got the log output, we need to again do an exponent to bring it to delog it, right? So that's what we're going to do in this case. So now these are the functions which we have created. Again, these functions, I'm pretty sure you might have already kind of created or used a lot during your machine learning course. There's nothing too kind of fancy about them. Then after that, we are going to build the one hot encoder, and when we are going to use consider text, maybe we may only want to consider the words in my one hot encoder which are occurring at least 3 times or more than 3 times. So that's the reason in this count vectorizer we are considering the value of mindiff as 3, so that this is something we can take care of, otherwise there will be too many columns going to come up. So the whole code is remaining whole code is basically to get that one hot encoder. Quite simple, you can walk through it. And once we get that, we are basically looking at the total number of unique words, which comes out to be 54,007. And when we will apply basically and definitely you can see that this is going to be huge, right? And the same way we're gonna create for response encoding, and for response encoding also we will ensure that the sum of all these probabilities should be equivalent to 1. That's something we have to ensure even in response encoding. So that's what we are doing it here. So after we have done it, maybe if you want to normalize the code, you can also do that. So that's the next step, we are doing it here. And once we have done this, this is how your values are going to look like. So you can see here that this is telling me that there are 5,732 values with which are kind of occurring, let's say 3 times, and similarly for the other, like the words which are occurring 4 times, 3,761 and so on. So this is the occurrence of word. Again, guys, I would strongly recommend you to go through each line by line, and we had made sure that we have provided all the comments to understand each and every line. You can see that for everything we have properly commented for you so that your understanding should be easier. But since they are very straightforward stuff, I'm not basically going line by line of code, because again, I'm assuming that you already know some portion of machine learning. But as I said, it's if you have any problem, just feel free to put it in the discussion forum. We will be more than glad to help you out with this. Now, once we are done with this, let's build the model. The model building stage is going to be very similar. Now, we have again taken the L2 norm, again the logistic regression. We are going to use calibrated classifier. We are going to use one hot encoding. And in the end, we're going to get this particular output. Once we get that, we can look at again the same graph to look at the minimum value for log loss for comparative alpha. Once we have done this, then we are going to compute our losses, log loss, and you can see that this log loss is coming out for test set as 1.25. In fact, it's much better in comparison to what we have got for the variation set also, right? So this is performing much better. That means this column is quite critical. And then once we are done with this, we want to look at the overlap portion. For that, we have again written a function, and the overlap is also high. So you can see that 96% here and 98% here for test and cross validation respectively, which means that my text column is highly stable and very much significant. So all these three columns are highly important. So that's what this basically tells me up. So now once we are done with this, we will do some more data preparation before we apply our machine learning algorithm, because now we need to bring all these three columns together to work and build a model. So that's what we're going to do as a next step. So we will do that basically in the next lecture. Okay, so after we have understood that all the three columns are important for building my final output, which is class, now we have to do some sort of data preparation and some sort of functions which we need for the overall machine learning algorithms. So what we're gonna do, first function is simply to just report back your log loss, so that I don't want to keep on writing this code again and again, because we are going to build various models like naive Bayes, Ken, and logistic regressions and so on. So I don't want to keep on repeating the same functions, same code again and again, and that's the whole reason we are writing it up. Second is plot confusion matrix. And if you do recall, this is exactly the same code which we had already seen it earlier when I created random basically model. So what I have just done, because we have to do create it again and again, now I created a function for it so that we can again and again recall it. And the role of this function would be that it's gonna give you back your precision, recall, and your accuracy, means your confusion matrix. So all these three matrix it is going to return, and if you look at it, exactly the same code. You can see that we have A, B, C, and these were exactly the same thing what we had created here. And the same function I'm going to call it in predict and plot confusion matrix function. So you can see that I'm calling this function here, and this function is doing nothing but it's gonna help me to do my prediction part, because my prediction code is also going to be common for almost all the algorithms. So that's the reason it's better to create a function so that I can use it again and again. Now, further to this, this is the function which is required only for naive Bayes, so don't bother about it much. It's just gonna tell you for a given index, and it's gonna print that what is the name of that particular feature. Okay, and we will also check whether the feature is present in the test point text or not. So this is a very simple, straightforward function which is just gonna we can see that it's written in if else loop, just to kind of look at and tell you that whether it's present in it or not. So we'll see in the naive Bayes part. Now the next thing is we got gene, we got variation, we got text. We have converted them to one hot encoding. We have converted to basically different sort of encodings here, right? We have done the imputation also, so with the response encoding, but here we need to combine them up. So we cannot just leave it as it. So let's say if A is one, basically this sort of value, B is this value, I'm gonna combine them up, right? Just think of it like this. Let's say the first vector which you are seeing, this one, let's assume that this is your gene, right? And let's say this value is your let's say variation. So I have to combine them like this, right? I need to stack them so that, you know, now this column, then this column, so concatenate these columns. So that's what we are going to do here, and we can do it with the help of hstack function. Once we go ahead with this, so this is gonna just create this, and I'm gonna concatenate both the type of calls, one gene, variation, and text for response encoding, and one combination we will do for one hot encoder for all these three types. So once we have done this, you can look at it and we can get this particular output, and you can see the shape of this part. So you can see here that for the train data one hot encoding, when I did, I got 56,201 columns, which is huge, right? Even my rows are lesser than the column number, and it's obvious because if you remember, my text column was having huge number of columns, and that's the reason in the final output I have this. But if I do a combination with the response encoding, I have only 27 columns because 999 for each, and that's the reason we do have only 27 here. So we are done with this, and after this we're gonna look at building the machine learning models. So we got our data. Now we will start shooting with respect to naive Bayes as our first algorithm, and we'll keep on comparing the results with various algorithms and see how it works. Okay, so now let's build the naive Bayes algorithm on the all three columns. Now we are gonna include the gene column, variation column, and text column, all three together. Now it's quite simple. We are actually building the models from a quite a good time. So we have already seen that how to do all that. So with the naive Bayes, again we're gonna choose the alpha, and we're gonna use the multinomial NB class because that's what we use it for multi-class classification. And we're gonna again fit the model. Again we're gonna do all those probability part. You can see that we are using predict prober so that we can get the probability output, and here also we are getting the calibrated classifier for doing that, and we are using one hot encoding because naive Bayes is good when you work with respect to your text data, right? So if you do recall it on the text data, it's work good. So even you have a huge column, it really doesn't matter to naive Bayes because naive Bayes will still do quite well in that case. So in this case also we're gonna keep that, and we got all our log losses. So you can see that this is gonna return me log loss for various sort of alpha values, and we can check out this values. We can say that alpha 10 to the power minus 5, this is the value, and so on. Now if you check it, maybe my minimum value is occurring for alpha as 1, right? 1.28 is my minimum value. Maybe that is what we may want to choose it, and we can plot and also confirm the same, right? So this plot, as we are seeing it from so long time, we are also going to plot and confirm the same part. Now once we have done it with that minimum value, let's use it on the test data and see that how is my log loss comes out to be. So in this case my log loss for test data comes out to be 1.32. Now, one more thing we also look at is that for my train set, I do have 0.92, and for test set, I have 1.32. So this distance is okay, reasonable, not that huge. But let's say if my this log loss difference between a training set and the result what you got from the test set is huge. If the difference is huge, that means that on the training set definitely there was some sort of overfitting happening. So you need to go back and again look at that case. But here it's okay, reasonable, so we can accept this particular solution and go ahead. Now we got basically this part. Now let's test it on the testing data as well for this alpha, and we got this. Now what we are going to do when we are testing it up, we are also going to look at the confusion matrix, and let's see that whether it is giving us the better result what we were getting earlier with respect to your random classifier. So in order to do that, you can see this value, and definitely we want the diagonal values to be higher, and this sounds like it is giving me a good output. You can see that at the wrong places we do have a lot of 0 0. Yes, we do have some issues. For example, you can see this value 47. This is suggesting that there is definitely a good in fact we should look at this value. So this is definitely a wrong classified points which is happening, but let's look at this from the precision point of view. Precision gives us a very good idea. Ideally we want this diagonal value to be 1, but if that is not happening, it's okay, because in the ideal case that never happens. So here let's say look at this. So definitely there's a huge confusion happening between 2 and 7, right? And we also have a confusion happening between 3 and 7. So that's what is one of the case we can look at. And even at few other cases also if we see, but majority of the value are okay, right? They're not very much getting confused, and you can see here with this model we are getting a quite a good matrix at the diagonal side. So that's what is happening in this case. Let's go ahead and see further things. Similarly, you can also look at recall matrix, and in the recall also you kind of see the same trend. like few places it is getting confused. Definitely you can see this 0.3 key, that means there's a confusion between 9 and 8 class, right? So that's what is still happening. Definitely we cannot come up with an exact good model. It never works that way. So that's something which we have to keep in mind. Now one more thing to look at is the interpretability, because if you do remember your business case, so business case was telling you beforehand that your model should also be interpretable, that you should be able to tell that why your model is predicting this. Now for doing this, if you remember, we have written that function above, get underscore important feature underscore names. Now in this part we are passing our data point, and you can see that let's say if I have taken any of the index where I got the prediction as 4 and my actual value was also 4, that means my model have predicted correctly. And the reason we got this as because we got the probability as this, right? So this is for 1 class, 2 class, 3 class, 4 class, 5 class, 6 class, 7 class, 8 class, 9 class. Now I can see that probability for the fourth class is highest, which is around 68% in comparison to all others. In fact, if we look at the further probability which is even close to it, is quite far, right? In fact, all the values are very far. Even this might be close, right? 0.08, which is almost just 8%. So this means that it is working really well here. But there might be few scenarios where might be this is, let's say, 0.68 and or maybe this is 0.5 and the second one is 0.4. Then it's quite close. Then in that case, even though we are getting the correct output, but we may want to look at again that what can be possibility. There is a confusion, so maybe you may want to look at those outputs because errors can be very expensive. So with this probability, you are getting a very good idea that how confidently we can say that, okay, whatever results I'm getting is really a good result or it's just a myth. Now you can see that here it is telling that basically we do have this point being present in this. So like we do have there's 10 text feature, function, protein, amino, experiments, all these are present in the test set. That's the reason we are saying that this belongs to this. So we are kind of giving the evidence that because these words are what we are seeing in this test data, that's the reason we are kind of going with this probability to be higher. So this is also a good idea, because now think from a pythologist point of view, he will be able to understand this word. Maybe I will not be able to understand all this, it's too naive for me, but basically the pythologist will be able to understand, and by looking at these words he can basically get a good insight that basically whether why this confusion is occurring or why my model is predicting it to be the basically belonging to that particular class. So that's how we gonna get this particular output. So this is about the interpretability part. Now you can look at some data points again. So let's say I choose another data set. Here also we got the right output. So you can see that predicted 7, value 7. So like this is class 1, 2, 3, 4, 5, 6, 7, 8, 9. So here also you can see that my probability is coming out to be 64%, which is again quite good. So that's the reason it is predicting correctly. But you can again go back to your data set and look at any wrong classified data, which I'm also going to show you in further models as well. But you can see that why it is giving you the wrong result. You can look at the probabilities and see that maybe there might be some confusion due to which this have occurred. So this is a very nice case of looking at this. So again repeating what all we have done. So this is basically about your naive Bayes. So again repeating what all we have done, and what does this basically tells us? That naive Bayes is working pretty well, right? So basically we do have computed the naive Bayes by starting at looking at the building the model. We created all this log losses, then after that we created this particular graph, and then we looked at all this log loss for each with respect to this, and then we calculated the log loss and created a matrix. One more thing which I also want to add here is, you can look at this, that this portion is also telling me the misclassified point, means if you subtract it with 1 minus this value, you're gonna get your accuracy. So I am getting almost like 0.38, which is almost like 0.62, right? That is basically is my accuracy. Definitely this is not the best, but let me tell you, this is one of the hard problem. Okay, this is not an easy problem. This is a very hard problem basically which we are solving. And though definitely if I say I want a perfect model, might all the diagonal values goes 1, and I would be more than glad and say that okay, this is the best model, means because this is what we definitely expect. So we have not yet reached to that level that we can definitely create an exact model which can give me 100% prediction. But trust me, if you are getting in this particular case an accuracy around 68 69, it is actually quite good. So that's the advantage of basically working with these sort of things. In machine learning, you can at least have a prediction something better than just doing a random guess. So and here we are talking with respect to 9 classes. So here, if you are able to come up with this level, it's quite good, and plus it's a real data. So do not forget that it's not some made up data which I'm using in the class. So this concludes our knife base, and we got a fair idea that what is the accuracy coming out, what is the log loss. Log loss is far better than my random basically part. So that means that this is working quite good. Great. Okay, so now we're gonna build for logistic regression. In fact, this is one of my favorite model because it's quite simple and can give sometimes very good results. Now in logistic regression, this time what I'm gonna do, I'm gonna do some oversampling. Why I'm going to do oversampling means what is happening here that we have noticed earlier that we had a lot of data in class 2, class 4, class 6 and so on, but there were few classes like class 8 and class 9 where we had very less data. Now due to this also we can have some impact. Now in order to resolve those impact, what we will do, we will try to balance the class. So there is a parameter which you have to just pass, and it will help you to oversample. It will automatically just do a oversampling within the data and will balance all the class for you. So this is what basically do. Now if you look at this, so I'm going to create this logistic regression with both, one with balancing and one without balancing, so that you get an idea that what is going to be the difference between them if we balance the data set for all the classes and when we don't balance it, right? So that will be very interesting. So again, the same thing. Now I'm going to use one hot encoder. So again, the same thing. If you look at it's a LR technique with balancing. But one thing about LR is that you can work on the high dimensional data. So that's the reason we will go back to one hot encoding. Okay. So you can work with basically with this very well. It have no issue with respect to this. So now let's go back and see. So when we are balancing the class, you can notice here that we are getting basically this sort of log loss, and we have to look at the minimal. So it's very difficult to see it from here. So let's do it from here. So the minimal, the value we got is 0.001, right? So let's see to this. So even if you look at it, you can see that it's 0.001, and this is the place where my log loss is 1.10, and remaining log loss, you can see it's pretty high. Now if we draw a plot also, it's telling me the same thing. 0.001 we got the minimal log loss, and here we are just basically looking at a training test and this loss. So I'm not going into all these basically line by line of code, because again we are seeing this again and again lot of time, and you can see that we are again and again following exactly the same thing: SGD classifier, calibrated classifier. So we're not putting any such different things in this case. So we got the values here, and we got 0.61 as my train loss. So let's put it up here. 0.61 is the train loss. For my cross validation, I got 1.1. So let's put 1.1. And for my test loss, we got 1.06. So I got 1.06. And let's look at the misclassified point here. So if I come back and look at this, we got 35.33 as misclassified point. 35.33 as misclassified point. Now by now you can see that though my log loss is lesser here, right? If you compare this, definitely log loss is less, but definitely misclassified points are little more in this case, right? So misclassified are coming higher in this case. Here we have 33.83, here we have 35.33, right? So they are almost matching up, but let's go ahead and see a few more things before we can conclude anything up. So I don't want to do any conclusion here that my LR is working better than KNN also. But if my metric is going to be log loss, then definitely my LR is doing better. right? If that is going to be my metric, because that's what we want to basically hold in this case. So let's go back and again look at few more things. Like, we have got this data sets. Now we got our log loss, and one thing which I want to show you up, that how you are putting into the code, that it's basically going to be balanced. So you can see that when you put your SGD classifier here, we are basically putting the balanced here. Okay, class weight as balanced. Just you have to pass this parameter and it makes your class balanced. So it takes care of all the overfitting and all that for you. Second thing is, you can see that the loss, I have put it as log. So basically when you say loss as log, it means that we are talking about logistic, because that's a logistic loss. So logistic loss, basically when you put, it's a logistic regression. But if I would have just changed this loss to hinge, then it would have become an SVM classifier. So that's the only difference between them. And you can see that in calibrated classifier, I'm always using almost sigmoid and it's all working, right? So that's a small change which I also wanted to kind of focus on. So once we got that, let's look at the confusion matrix. So my confusion matrix came out to be again in the same way. So you can see that we can see that we do have a good high values coming up basically on this part, and we do still have some concerns with respect to 7 and 2, but that's okay. There will be definitely some points, but definitely is doing far better. So again, this interpretations, now we have learned a lot, so we don't need to bother much about it. So we almost every time we are getting same. Now here, one more good thing about logistic regression is that it's very good in terms of interpretability. So when we talk about interpretability, it's kind of awesome. So in that cases, it's because it looks at the weights and all that, and based on those weights and coefficients, it basically gives you the interpretability. So this is a very simple function for achieving the same. And when we have done this, you can see that we are going to import this and again look at the interpretability. So even you can see that by my predicted class 7, we have gone through this multiple times. So I can see that for the 7th probability, we are getting 87.62, which is awesome, right? That's the reason my prediction is coming out to be 7. And these are the reason, like you can see that we do have 35th feature which is activated present in the test point. So this is basically the interpretability part. Even we can also look at an incorrect data where we do have predicted class to be 6, but the actual class was supposed to be 4. And you can see that here, definitely if I look at it, 1 2 3 4 5 6, we got 48.27%, and that's where it got confused. But one very interesting thing, if you note here, that it's all, this is the place where this gets interesting. You can see that though my interpretability came out to be bad, because here since my 6th class was having 48.27 probability, that's the reason my basically it returned you that okay, it's a class 6. But at the same time, can you notice this part? Class 4 was also having 42.29, right? So definitely by looking at the probability itself, we could have said that yeah, there is a good confusion happening between these two classes because they are very close. So that's where it got, but it's not always going to be the case. Okay, so keep that in mind. It's not always going to be the same case where you are going to notice that it's gonna give you close probabilities. There is a chance that maybe one of the probability which you have predicted wrongly may be very high, but still it is going to give you wrong results, because again, machine learning is not a god. It can bring you closer, but you cannot say that it's going to give you the perfect results. Now let's come back and see a few more things. Now we have just seen it with respect to class balancing stuff, but what about if my classes are not balanced? I don't want to go with that parameter class balance set. I don't want to do oversampling here. So in that case, if we go ahead and look at it, we do getting basically some sort of this again the same part, and we can see that it's going to be minimal for 0.001. So let's go and check that. So we are going to get 0.001. Yes, we have 1.09 for this, which is quite less. And then we have computed again our train loss and this. And if you look at this, we are nowhere using the balancing part here. So the balancing is not true in this case. So in this case, we are getting the train loss as 0.61. So let's note down. So it's going to be 0.61, which is same. And this is for LR without balancing. Okay, and again we are going with one hot encoder itself. So this is what we have got. Now let's look at the cross validation. My cross validation comes out to be 1.86. 0.86. Can you see a red flag? I hope you can. And we do have, I'm really sorry. I have written down the wrong term. It's 1.09. Okay, that's why I was thinking that it's a red flag. So it is going to be 1.09, and if we go back, it's going to be 1.07. So we got 1.07, and let's look at the misclassified points also as well. So if we go back and look at this, my misclassified is 34.77. 34.77. Definitely it's working better if I look and compare with respect to my width balancing. Okay, this is interesting results of machine learning, right? Sometimes it do happens that you can, when you thought that balancing will help, but it didn't much, right? Though the misclassified point have kind of reduced. At the same time, basically here if you look at your log loss is almost coming similar, right? So you can see that for KNN and both the LR, my log loss are very similar. There's not much difference here. So maybe we can go again with respect to whatever we want to. So, but this is giving me a good result. Means I cannot say that LR is working bad here. But definitely we would like to see other classifiers also, to see that if they can somehow perform better than them. So we have to still wait for that particular moment. So now let's go back and let's look at few more things here for this. Again, you can look at the confusion matrix. For confusion matrix, still we have some confusions happening, but there are few classes which are getting now very nicely classified with the value 1. Even for class 9 we are getting the value 1. And you can also see that these values are also higher, which is good. There are still confusion happening in 3 and 9 now, and 2 and 8. Okay, so there are still confusion, but you cannot skip that. At the same time, now let's look at the testing some points. So if you look at the testing, my predicted is 7 and my actual is 7. So let's go and see whether it's what's the value. Yes, and yes, you can see that this is the lower value. So that's the reason we are sorry, this is a higher value of probability. That's the reason we are getting this value. So it's almost going to be 86% probability, and we got the perfect output in this case, right? So, and this is the interpretations. We have already talked about interpretations a lot, so we need not repeat it again and again. So we got basically this result with respect to my LR results. Now, further to this, we are going to look at SVM models. We will see that how linear SVM is going to work in this case. So now we're going to move to linear SVM. Linear SVMs are very similar to what you have with the logistic one. So in fact, let me note down, this is linear SVM. Now, we are not going for RBF SVM because first of all, we don't know the kernel here. And if we use RBF, they are not very interpretable. So as per our business requirement, we want the interpretable result. So in that case, we will not be able to go with respect to kernel SVM part. So let's keep it linear, and that's going to be very similar to logistic regression. Only the loss function get changed from your logistic to basically hinge loss. So that's going to be the only difference. So let's see that if we just change this loss function, is it going to have any impact here? Now, if you look at this, again, we can go with one-hot encoding because since it's just like linear, so it's also going to work quite well even if you have a huge dimension data. So we will go with respect to this, and you can notice here that again we are getting for 0.01, we are going to get the minimal loss. You can see that 0.01 we are getting the minimal loss in this case, which is 1.13. Remaining are very high. Now once we put this value, we got the log losses and also we also got all this train test loss. So I've just put every code into one container here. So here my train loss is coming as 0.74. So let me note down, 0.74 is my train loss. Now further to this, let's look at my CV loss, which is 1.13 and 1.14. So here I have 1.13 and 1.14. Let's look at the classification error. So my classification error is going to come out to be 34.21. So let's go back, 34.21. So here you can see my log loss have gone high, right? So that was my main criteria. Yeah, definitely you can see that this have gone low, but at the same time my log loss have gone little higher. So I would still not consider it for my final step, though it is not bad in terms of classification if you see that, but still for log loss even for 0.01 it may have a good impact. So let's go and check the confusion matrix. So this is my confusion matrix using which we have anyway got our accuracy and all that. Now with the precision recall, you can see that values are higher again, but yeah, there are some confusion points which have gone here, right? So you can see here that now the confusion is between 1 and 4, but it's not that huge. Even from recall, you can see that we do have confusion between 2 and 8 and 4 and 9. This remains the same. So now after that, let's classify some points. So when I classified for 7 and 7, you can see again the probability comes out to be pretty high for this. That's the reason we are choosing this up. And this is also an interpretable model, and that's what we are getting in our output. So this is again an interpretable model output what we got. Now further to this, we will look at random forest. Now let's talk about the random forest point in the next lecture. Okay, so now let's talk about random forest. So in random forest, though it will be good idea if you go with response coding, but sometimes even one hot encoder works well. So, but definitely we want to like to keep the dimension less. But let's do one thing since it's a very good model in fact, because it tries various things up. So I would suggest you to go with one hot encoder as well as response both, and we will see that how my results will look like. So what we will do with this model is with one hot encoder part. So we are having two hyperparameters this time. So one is going to be a depth and one is going to be an alpha parameter. So now what we're gonna do for this case is that number of estimators we're gonna keep and the maximum depth we both want to find out. So definitely this algorithm may take little more time when you're going to run it, because as you are aware, random forests do take some time when you're going with this. Now what we are going to do, we are going to put this and we are using the criterion as Guinea, and we are fitting the model again using calibrated classifier. We are using the log loss. Now we are getting this result. Now when we are seeing this result, you can see here that my basically my value I need to search that which is going to be the best. So for 200 best estimator, we are getting the log loss to be minimal. So let's go and check that. So if you look at 200, you can see the log loss is 1.14 and the remainings are pretty high. Now you can see here that with this value we have calculated our train test and cross validation loss. So let's put that. So for train loss we got 0.71, and so let's put it. So 0.71. So the space is filled up. So I need to create a new table now. So here I'm gonna say random forest, and this is for one hot encoder, and this is going to be my train loss. I do have a test loss, or in fact again I'm doing the same mistake, cross validation loss. I have a test loss and misclassified points. So this was 0.71. Let's go back, and we do have 1.14 and 1.12. So let's put it 1.14, 1.12, and let's put the number of basically this is the point which we have got in this case. Now if you compare this particular portion with respect to your with your previous outputs and all, you can notice it that we are definitely not performing that well in comparison to the last part, right? So if I go back to my earlier page, we do have got the log losses of 1.06 and all. So what we will do, we will explore this component again in the next lecture. And also what I'm going to do in the next lecture, I'm going to also tell you up that how to work with this log basically with respect to this log losses and all when we are using the response coding, and we will see and we will compare both of them and see that how well it is working. So we will do that in the next lecture. Okay, so in the last lecture we were talking about random forest with one hot encoding, and we have already seen that when we got the best hyperparameter, there were two hyperparameters, one is depth and second is estimator. And then further to this, we got our training and test losses. Now we were also looking at the misclassified point, which got around 0.38. So let's go and put that. So there were two values. So here we're gonna keep it 0.38. So this number have also increased, right? Now, definitely this is not doing that well when we compare it with respect to other model. That's surprising, but yes, it's not working. Now let's come back and see a few more things here that basically we will calculate the confusion matrix and all, and again you can see that there will be few confusions, but other than that it's all same. Now it's very simple way to basically for you to go back and look at this precision and recall. I'm not going for every kind of explanation on this because it's quite simple now. Then further to this, we can also look at the classification points, and you can see here that we have correctly classified this, and the reason is again the probability was 60.4%. Again, when we say about random forest, it's quite good in terms of interpretability, so we are getting a nice interpretation about our results as well. Now what we're gonna do, we're gonna follow the same random forest, but this time with the response coding, and let's see the results what's gonna come out to be. Again we're gonna get the hyperparameters. Once we got the hyperparameters, we will get the log loss and all that. So let's put it, so train loss is coming as 0.05, so let's put it 0.05. This is random forest for response encoding. So 0 point, this is quite low, right? So let's go back and see whether what's the further result. Now this is 1.2 and 1.3. Okay, immediately reject this model. Reason being, you can easily see that 0.05 and 1.2, there's a huge difference between them. That means there's a huge overfitting which have happened in this case. So definitely this model is not good, but let's still see that what is the value of classification we're gonna get. So let's go back and see it. So it's coming as 48.68%, which is again bad, right? 48.68. So again, this is telling me up that again this is a worst model which we have seen till now, and random forest is definitely not working good, not even for one hot encoding, but response coding encoding was even worst. So this is how we can see this part, and further to this, again we can look at this matrix part, and we can again classify and do the interpretation with this. So this is how you can kind of look at and basically get your interpretability and get your query point classified. Now this is interesting, right? So we got a good table with almost all the algorithms which are available. We will still do one or two more things, but we have almost covered up all the algorithms, and few places I've gone with one hot encoders, few places I've gone with response coding. I would like to give you as a homework activity to get this even more better. I would suggest you to please go through it and try it wherever I have tried only with one hot encoder. Please try to do it with response coding. Try to create a table. Keep writing all those things with you, and same way keep on doing for all the algorithms like that, and see what the results comes out to be. Right. So I have just chosen whichever I feel is the best, just to show you up that how it behaves. So this is the way we gonna get the results till now. So great. In that case, let's connect in the next lecture for one more further thing. Okay, so now we're gonna build the stacking model. So this is also one of the is ensembling method which you might have learned during your machine learning courses. Now, in order to talk about this ensembling methods and all, what you do is, let's say you generated three different models, M1, M2, M3. And using those models, you gonna generate basically you're gonna put this output to another model, maybe LR, and then get the output. So this is how basically we do it. But there are some problem with this. So when we generate these models, we don't take the whole data set, we take the subset of data set D dash. So we do take different data sets, so it works. Now the problem with this particular code is, though this basically this is called a stacking method. Okay, now the stacking method works very well if you have a huge amount of data, but if you do have a very small amount of data like we have in this case, this may not work that well. So that's basically the problem with this. So since here we do have a small data, maybe the stacking model will not give us a good result. So you can see here that here basically we got the we are taking basically some models, and you can see here that I'm only taking my SVM because I'm taking the loss as hinge loss, and I'm taking another part which is basically my naive Bayes, and I'm doing all these things on one hot encoding. You can always feel free to do it on response encoding. So you can see here that we have chosen basically three models, and one is we have also chosen logistic regression. So logistic regression linear SVM, and naive Bayes. These are the three things models we have built, M1, M2, M3, and after that we are going to build our stacking model. So this is quite simple, and once we got this, we can just look at our final log losses. So definitely you can see here that it is coming at 0.35, which is not that good if we compare with our older one. So if we go back and look at this, we already have got lesser than basically 0.35. We already have the KNN which is giving us. And at the same time, if we also go back and look at the log losses, so log loss is also coming at 1.11 on CV and 1.1 on this, right? So if you go back and compare, so definitely it is more in comparison to my these two loss. So I need not write it in my table now, because as I can easily see that it is not performing well, and that is what we were expecting also before, right? Because if you look at these log losses, definitely these log loss is not going to come to be good, because the reason is the data was kind of smaller in this particular case study. Now there is one more thing to look at after this. So once we have done this, we can also see the maximum voting classifier. As the name states, that it looks at, let's say you create three models, and from three models, whichever the log loss is going to be minimal, you're going to choose it. So that's a technique what it use. And again here you can see that we're gonna log loss by 0.19, but again you can see that my log loss is pretty high on the test set, 1.20. So this is again going to be very high, because we already have got 1.06, which is the minimal with us. And even if you look at the cross validation errors and all, this is also going to be higher. You can see that 0.35. Let's put this value 0.35, but we do have already lower value than this, right? So we need not again put this into this. So again, if we have to decide the clear winner, again we have to take a call now based on our evaluation criteria. So by the evaluation criteria, we should go for LR, which is one hot encoding with balancing, because we are getting 1.06 as my lowest value in this case, right? So it depends. If we are looking for accuracy, then my answer may change to KNN, because that is giving me 33.83. So it again depends on case to case. So like when we talk about, let's say, and when we talk about competitions like Kaggle, then in those cases we all kind of only target with respect to one parameter which we want. So there will be, you if you look at a leaderboard, somebody will have 1.07, somebody will have 1.08, somebody will have 1.06, like that. Okay, so whichever is going to be the minimal is going to be the winner. So that's how basically it works there. So with the testing data, they always look at and just kind of keep working on minimizing this parameter and see if they can basically win those competitions. This is how it works. But at the same time, what we have done in this exercise is very minimal. To be really frank, you can also do a lot of stuff. For example, on the text data which we have looked at, we very quickly kind of went to bag of words, right? We just used the const vectorizer and kept on working on that technique. But definitely you have so many things, like you could have gone to TF-IDF, you could have done so many other ways of splitting this data. Even the models what we have used some model with a basically response coding, some model we have gone for one hot encoder, though it is going to work in the same way. But still you can go ahead and even build those models with all the ways possible and see that which is going to perform better. So all these things you can anyway try. This was our attempt to give you an insight that how you can basically play with these kind of algorithms and basically come up with some solution, and even can target Kaggle competitions like this. But in real world case, if you're talking about, definitely you're not going to run behind just one metric. That's the reason I have also taken the misclassified point for you, so that because in real world even the accuracy matters a lot. So in those cases we will be looking at the other stuff and do it. So in this case maybe we can give linear regression with balancing and say that okay, you can go ahead and use this into your production system, right? So this is the final output with this. So I hope you had a good learning with this particular project. Please give a good attempt to it. Please look at all the interpretability code which I have not explained in detail line by line, but definitely from your machine learning courses you might have already an insight how to do it up. If you feel that you have a better solution, please do it, and even let other people know. That's something which will also encourage. The main idea was to give you a good insight how to approach these problems, what are the parameters we look at, even what are the optimization technique we do, how to play with these hyperparameters. So these were the main motivation to look at this particular project. Thank you.